Innovation and Research or PAIR program is a flagship innovation by Anusadhan National Research Foundation designed to elevate India's research capability through structured hub and spoke mentorship model. Under this fantastic initiative, we have a highly relevant and exciting topic lined up for you this morning: agentic reasoning for scientific application. To lead this session, it is my absolute pleasure to introduce our distinguished speaker, Dr. Bharti Chatterjee. Dr. Chatterjee is an assistant professor in the Department of Computer Science and Engineering at IIIT Delhi, where he is closely associated with Distributed Computing and Learning Lab and the Infosys Center for Artificial Intelligence. We are very lucky to have him here to walk us through the applications of agentic reasoning. Please join me in welcoming Dr. Chatterjee, sir. Thank you for both being here. The virtual floor is all yours.
Thank you. Thank you very much for the invitation and the introduction. I'm really happy to join you all this morning. I wish I could have been there, right, to join you in person, but hopefully in your next meeting, we'll see if I could make it too. But thanks again for inviting me. Okay, so I believe that as much I have heard from Sastry sir, right, that this is a gathering of people who mainly come from science domain, right, drug discovery, chemistry, and so forth. But again, my apologies if I do not have entire idea of the gathering. Regardless, so I mean, very little bit about my background. So, of course, I come from distributed computing, distributed algorithms domain. That's what I did my PhD on, right? But since then, I have been mostly doing this distributed machine learning, right? So, my primary research area at this point is to train large models on distributed setup on supercomputing environment, right? Design algorithms around them and do even the engineering part. The same interest also leads me to a couple of other domains, in particular the agentic coding. So this semester I'm actually teaching a course on agentic reasoning, and today I'm actually going to present material from a paper which is not mine, as I have posted here. You can see on the title slide. This is work from a group of researchers that was published in ICLR 2025, an agentic framework for chemistry research. I believe that many of you can relate to the work that is presented here, right? But yes, I cannot claim. I mean, my work, which is now under submission in this domain, is on coding. But I thought that it would perhaps be more relatable if I present something on chemistry. Okay. So having said that, I would just like to know. I mean, maybe anyone can say that how many of you have done agentic coding? I believe that all of you have done programming, right? At some level or another, maybe MATLAB, maybe Python, maybe R. But given this last 2-3 years, the prevalence of agents in scientific coding as well, right? Any prior familiarity with agentic coding? Okay, so let me then take it as a sort of maybe first intro to agentic coding, right? So, well, I mean, what I could do is that I can actually show you, very briefly. Unfortunately, just before this presentation, I tried to check whether that the codes. Okay, instead of speaking, let me actually show you the code, and thereby I could actually give you some context. Okay, and after that, I will return to this window, right? So yes, so I hope that now you can see the IDE. This is anti-gravity IDE. This in itself is an agentic IDE. If you have not been using it, I would really encourage you to give it a try, right? So of course, at this point, anti-gravity, I believe, is sort of taking our data as usual. All these big companies and models are just to grab our data in some sense or another, right? So therefore, anti-gravity will not be available if you use your institutional email ID. But if you use your personal Gmail ID, anti-gravity is available, and it makes coding real fun, right? That's it. So here is a code, right? Agentic code example, and right. So yeah. So this is a very simple chatbot example, but this example will be absolutely relevant to the paper that I will be discussing immediately following this one. Okay, so what I was saying is that I actually demonstrated this code in my class, right, in one of the lectures. But unfortunately, this morning I figured out that somehow my Anthropic key is misplaced, right? And this is not working. I wish that I would have actually checked it yesterday, and then I would have actually used another key. But my apologies, I cannot run it right now. Regardless, let me tell you what is happening, or sort of a generic way of writing an agent. Okay, so. Well, I mean, what is an agent? If I could give you some definition, right? So then it is. There has been a paper on defining the agents, AI agents. So there is a very layman but very apt definition of agents is that it is just a loop, a program which runs in loops, right? Where intermittently you have LLM calls. So essentially you have LLM calls in a loop, right? And all sorts of other things you do as much as possible. But wherever you feel like something can be passed to LLM in terms of either using its knowledge, right, from its parametric memory. At the end of the day, what is an LLM? I mean, I believe that we all understand that LLM is just a function. Essentially, this is a neural network, a deep neural network function, right? Which is a parametric function. So, in its parameters get trained, right, over a large corpus of. If it is language model, then over a large corpus of language tokens, right? And thereby the parameters, those function parameters, store some memory. We call it parametric memory. So it has knowledge. Beyond that, when we say that LLM is doing reasoning, so these days all of us can see when using Gemini, DeepSeek, or whatever, right? It has entire reasoning trace or its thinking trace, right? So where exactly that is coming from? Absolutely from the same way of generating the next token, right? So it is trained on data which we these days it is also very well established for reasoning data. So all that happens is that, so suppose you are solving a maths problem and then you arrive at the solution, and then you have certain steps of arriving at that solution. So when you train the model, your data should not only be having the final answer, but also the entire trace. Once you train a model with trace of how you arrive at a solution, which is called reasoning data, more precisely it is called chain of thought data, right? Then your model, when it generates output, it also shows the trace that how it arrived at certain answer, and thereby you see the reasoning behind arriving at that answer, right? And thereby we call it a reasoning model. Okay, by the way, I must put this one as well. I mean, customary thing that please feel free to interrupt me wherever anything is not understandable. And yes, I'll be more than happy to answer any doubt or query, because at this point I cannot even see your faces. Usually what I do that in a class or in-person presentation, if I see someone's face has some integrate, expression, then I usually stop myself and then ask, please feel free to ask me something. So yes. Okay. So then idea is that, like I said, that a loop, and then in that loop there will be LLM calls in between. Okay. So you also would have seen that these days when we are using Gemini and everything, right? Essentially they stop and then actually they pose another question that, okay, would you like me to help you with something? So this is loop. Unless you close that window or something, it will keep on looping by sort of stopping by somewhere and then asking another question to do another prompt, thing like that. Okay. So coming back to this particular example, again I must sort of declare here that this example is directly taken from Andrew Young's course on LLM agents, right? All credit to Andrew Young. Okay. So idea here is that using these are also called in agentic terminology, these are called tools. Archive, for example, is a tool. Okay. So using this archive tool or API, number of papers are downloaded, right? And then idea is that using these papers, we want to sort of generate some kind of an abstract, right? So collect a number of papers and then generate some kind of abstracts, right? I don't know, maybe if you want to write, let's say, a short abstract for submission for some conference or something, perhaps this could be like a very ready-made tool. So just go and then give some certain topic, right? And download number of papers from archive, and then create one, short abstract. So you can see that I have used the archive tool here, and then another tool is this .env, right? So this is just to set up the environment for an agent, and Anthropic is actually the LLM service provider, LLM inference provider, that is here. And then a directory is created named papers. You can see that directory here, right? Yeah. So here is this papers directory that gets created. Okay. Now, after that, this first tool searches for relevant archive papers based on topic and stores the papers info in a JSON file, right? So here you can see this papers info.json. So it will just save a metadata about the file, very much similar to perhaps you have your BibTeX entry. So here the topic that I searched was, I believe, computers or something, and therefore, computers, and therefore, this is a very generic topic, so it has downloaded just meta info about a few papers, in fact, 5 papers to be precise, and then saved that in the JSON object. If I let's say do here, right, so let's run this cell of this Python notebook, right? And after that, let's search something like, I don't know, maybe organic chemistry. Okay, and yes, right. So there are like now these many papers, just meta info saved here. You can see that organic chemistry folder is created, and papers info.json now has saved info about these papers, including its summary. So summary is important. It is kind of taken from its abstract. So that is provided by the Anthropic tool. And using these summaries, we can create this abstract, our desired abstract, right? So low frequency dielectric loss of metal insulator organic semiconductor junctions. So of course, these are random. It could be made more precise. Okay. So search papers from archive, and these 5 papers are saved. Okay. Now extract info. The second tool looks for information about specific papers across all topic directories inside the paper directory, right? So so tool in the parlance of agentic programming, it could be like either tool which is provided by some let's say tool providers such as archive and others, or you write yourself some functions. So functions that are written by you to use LLMs, right, for your desired purpose, these are also called tools. So for example, here is a tool written by the name extract info, and then all that it does is that search for information about a specific paper across all topic directories, and then paper ID and JSON string will be returned from here, right? So let's run it. So now this tool is defined, and now let's extract info from a paper let's say for this paper's ID, we want to extract info. Right. Yes, so here is the info, low frequency dielectric loss, whatever authors are so and so, then summary so and so, right? So that info is gathered. Of course, this tool is written sort of in a very nice way. We can always write it in a better way. Inside the tool we can call other tools, right? That are also provided by other many such software tools. How to sort of shorten something, how to get something important, and so forth. Again, LLM reasoning can be sort of used for that, right? So here is tool schema. Tool schema is part of an agentic code, right? So there you write that what kind of tools are available for LLM for the agent to call. So for example, search papers is a tool, right? That is available, and it by in turn it called the archive, right, as a tool. So search paper is a tool, its description is given. Similarly, extract info is another tool, its description is given, right? So here is this tool schema. What happens that agent follows this tool schema, right, to use certain tool when it sort of needs to perform certain action, right? So that we execute, right? And after that tool mapping, so for example, search papers will be used for search papers, and similarly, extract info. So finally, this extract tool, this is about extracting the info and then sort of saving it for your purpose. Okay, now next is this chatbot. So let's run it. So this chatbot loads the environment, and then the client is Anthropic client. Here you can have any client. For example, these days we all are using API calls from Open Router and others, right? You can use any of those calls to create client. Most of the times we have OpenAI compliant client. This is Anthropic client, compliant client. Okay, and then there is this response. Okay, response is generated by this is just a definition here for response generation. So this is for process query, right? So we send certain text. We'll say send certain text, and after that query will be processed using this LLM. So this LLM calls it there. Okay, and this is this loop that I was mentioning. So agent is loop with LLM calls, right? So here we have this loop, chat loop, and here you can see it will, it is also defined. So here is some example. Now let's run this chat loop. Okay, and you can see that my chat loop is running, and it asks me to put some kind of query. So I don't know, maybe I can put a query that what is organic chemistry. Like I said, unfortunately, my code is not running this morning. Otherwise, it would have resulted answer. But let's see what is happening, right? So so error could not resolve authentication method. So essentially, my Anthropic's key is missing. The key that I had is just not working. But otherwise, if let's say I have my LLM key working, right? So it will return something, and then will again stop by to take further instruction from me, and thereby sort of execute it again by LLM call. So right. So then I can just press exit. Okay, I believe that escape will work now. So yeah, I believe quit is the command to get out of it. This is So this was a very basic agentic code where LLM calls are sort of made, right? So any query about or doubt or questions about this agentic code that I just showed you? I'm really sorry that I could not execute it right now.
So I think now correct.
Okay. Yeah, I think that's understandable. Okay. Now let me present the paper that I wanted to present. Okay, so that was agent, right, for sort of collecting archive papers, and thereby sort of collecting the summary, and thereby creating some kind of a short abstract, right? A very simple agent written. Here is an agentic framework for chemistry research. So let's see. Yeah, I'm not sure if in the audience anyone has seen this paper before, or maybe even otherwise some other similar papers. But yes, I hope that many of you sort of get something from this discussion. So LLMs for scientific discovery. Scientific discovery, which is, of course, we all know that a fundamental driver for progress, right? Both for society as well as the fundamental understanding. LLMs can accelerate the discovery process. This is now well settled, right? Although there are still many people who would often say that no, LLMs can only do up to something, right? At the end of the day, we are sort of the owners, but not sure. I mean, there is the other sort of contrary thought that says no, LLMs are actually capable of doing many things, right? Including sort of doing scientific discovery that is sort of very rapidly gaining ground. So key question here is that can LLMs move beyond text generation to genuine hypothesis formulation? Okay. So so before this work, this is still like 2 years old, and 2 years in this domain of LLM and agents is like almost an age, right? So this is one age past, right? Since this paper appeared, several more sophisticated agents have been now sort of made available, both in terms of proprietary agents such as deep research, alpha evolve, and so forth, as well as many open source works. Okay, so prior work at that time, I have put these papers citations here, not to distract you, rather to give you some pointers in case you are interested. Please check out this paper and the citations over there. Okay, so in social science, such agents were used, multi-agent systems that decomposes hypothesis into background concept plus inspiration concept. Okay, the valid assumption is that social science hypothesis relate an independent variable to a dependent variable, right? So I mean, if you want to if we little bit pause here and then try to discern here, discern this particular sentence, then it is saying that a hypothesis to sort of idea generation. So hypothesis, you can have certain hypotheses, right? In political science and so forth, you have certain hypotheses. These are independent variable, right? And then the dependent variable, which become then idea generation, right? In social science, every now and then, of course, social science people also come up with some ideas. Political ideas, I don't know, maybe communism. Hypothesis that everyone should be equal, and then that leads to communism. But all credit to them. Similarly, in NLP domain, large-scale expert evaluation confirms LLMs generate more novel but slightly less valid hypotheses than human researchers, right? So they are definitely novel, but many a time, of course, we understand that there is hallucination, and therefore its validity, right, is still in progress, right? In improvement. Limitation is that both efforts restricted to social science or NLP, natural science, at that point was unexplored. Of course, now it has been explored like anything. Okay, so this paper was investigating this question: how capable were LLMs for generating general hypothesis, for general chemistry hypothesis, right? And one in fact, the first stoppage, right, in the journey of journey of building any agent is the benchmark. So you create certain benchmarks, right, and then you evaluate on that benchmark existing LLMs or agentic frameworks and things like that, right? How good they perform, okay, and thereby you want to improve on that benchmark. So at that point, they also there was also lack of a standard benchmark or framework that could cover chemistry at the level of nature or science publication. Okay, so central research question is that can LLMs automatically discover novel and valid chemistry research hypothesis even at the nature level? Nature, the publication, right? We all wish to have papers there, given only a research background without restriction on the domain of the research question. And the insight derived from cognitive sciences that the key creative ideas arise from associating seemingly unrelated pieces of knowledge, right? All of us try to do that, right? For sure, when we are in a certain gathering and then we try to do networking, I believe that first thing that we start with that, okay, can we sort of have some kind of collaboration, some kind of mutation of ideas, right? So that's like creativity, a very natural first step. The background inspiration decomposition from social science extends to chemistry. So the inspiration is coming from social science, where different ideas people try to mutate to come up with new ideas or hypotheses. Difference is that chemistry hypothesis may require multiple inspirations. Example given: composing several components into a novel system. But at the end of the day, this was still up for exploration, and that's what this paper did. So here are the three decompositions of this whole, right? A bit more formally, right? So probability probability of certain hypothesis, coming up with certain hypothesis given the background, can be actually in terms of implementing execution or let's say derivation of this probability, that given certain background knowledge, how to come up with new hypothesis is a very costly, computationally costly sort of affair. Okay. So therefore, naturally, it must be decomposed into sub-problems. So here are the three sub-problems. Can LLMs identify inspiration papers relevant to a given research question? Very similar to the agent that I just showed you, right? That you sort of give some kind of keyword combination, and then figure out some papers, right? Available on internet. At this point, I just showed you how to use archive tool, but in the same way, you can use scrappers, web-based scrappers, and thereby you can collect papers. Okay, so yes, so identify inspiration papers for a certain research question. Given known knowledge, that is background plus inspiration, can LLMs infer unknown but valid knowledge, right? So which were either to unknown, but still that could be valid. Can LLMs rank hypotheses so that high quality ones surface to the top, right? So this is something those who are familiar with the LLM parallels, then this is something called inference time scaling, right? So what you do is that you generate a number of inference results. Here, in this case, generate a number of hypotheses, and then you rank it, right? Based on certain criteria. So ranking, of course, could be done by different tools, but LLMs are primarily used for ranking. It could be like a different LLM or same LLM. This is inference time scaling, and thereby you come up with the most appropriate hypothesis or most appropriate inference result. Right? So essentially, this problem of let's say if you try to do something like, okay, you gave one certain idea and then ask LLM to write entire paper. Instead, you break it into some subtasks, and thereby try to come up with new hypotheses and possibly write a paper. I believe that some of you would definitely have seen this agent archive project, but otherwise I will also show that. So what happens is that in a totally agentic way, ideas, you just give ideas, right? And ideas, based on that ideas, papers are collected, existing background is information is collected, and paper is written, and that is published on this agent archive. Okay, so that's how science is developing at this point. Okay, so together these approximate a set of sufficient conditions for the central question. The benchmark construction, like I said, that benchmark is the first step for starting an agentic journey, so to say. Right? So they collected 51 chemistry papers annotated by chemistry PhD students. Each paper decomposed into background, inspiration, and hypothesis. All papers, the collected papers were either from Nature or Science or equivalent in 24, right? LLM training data cutoff. So the gathered data that was so the LLM that was used, right? It was made sure that the version was being used which had seen data only until December 23. So this is a good concern actually, right? That data contamination should not happen when we want to verify the capabilities of LLM. By the way, everything fine because I don't hear any remark, any question, any interruption from there. So am I audible? Just for check.
Yes, sir.
Okay, cool. Right. So the data contamination was avoided. Design philosophy analogous to the mathematical Olympiad, a small set of very difficult but meaningful problems. Right. So going to the depth instead of going to the breadth. It introduces a ranking task for scientific discovery, largely overlooked in prior work. Right. So for scientific discovery, sort of generate many hypotheses, like I just said, inference time scaling, generate many hypotheses, which is of course cheap to the extent that you have enough money to burn LLM tokens, right? And but at the same time, experimental verification of all those hypotheses could be very difficult, right? It could be expensive. So then, can LLM be utilized for the ranking task that a particular hypothesis is better than the other hypothesis? And you have much better idea about the chemistry hypothesis than me. It could be even an experimental workflow to discover a new molecule, or it could be, I don't know, maybe a new let's say idea formulated into certain kind of I don't know, derivation formula, right? And thereby to come up with a new metric, right? The latter one is from physical chemistry domain, the former one is from experimental chemistry. Okay, so the framework that they name is Mooj game. I'm not sure why they use this Mooj. I tried to figure out if this has some full form, but looks like that this is mostly perhaps inspired by the moose animal, right? That's very common to see in Nordic countries. Okay, so framework and contribution. So it has three-stage multi-agentic framework. Search the literature. By the way, when we say multi-agent, it's like so. For example, I just showed you, one very simple agent where the archive papers metadata was collected and possibly that was summarized, right? It could be one agent that is like for literature search. Okay, you can actually make another agent. Agent will call again LLMs for leveraging inspirations, right? So it proposes hypothesis. So based on this literature search and then background knowledge retrieved, right? The LLMs will be further prompted to propose hypothesis for the background question, and there will be a third agent that will be ranking the hypothesis. Okay, again, agent will essentially be just doing some LLM calls with inside some function, the way that I just showed you the written function. So key technical contributions of this paper is that it uses evolutionary algorithm for diverse background inspiration association. It has this multi-step inspiration retrieval. It is another sort of novel thing. At least at that time it happened, right? It composes more than one inspiration for chemistry specific needs and efficient ranking method to prioritize hypothesis for experimental follow-up. Right. So first demonstration that an LLM framework can rediscover many innovations of nature science level chemistry hypothesis, which was contamination control. So more or less, by now I have given you an overview of this paper. Please feel free to ask if you have any question, or even please feel free to make this comment that it looks perhaps certain I don't know, not making much sense, something like that. Any question, any comment at this point?
No, sir.
Okay, yeah, very much expected. All right. Yes, I know that this is like a very easy thing, so it should not be sort of prompting you to ask some question. Okay, I also believe that going by the proposed time, I have roughly 8 minutes left, but I don't know. Maybe I can continue. I mean, I can stop at 10:30, but otherwise I can also continue for 5 more minutes. Okay. So multi-agent scientific discovery benchmark. So now here is the details of the benchmark. So the benchmark serves two purposes. It analyzes LLM's capability with respect to three fundamental questions: inspiration retrieval, knowledge inference, and hypothesis ranking. It provides a challenge, that rediscover nature level chemistry hypothesis given only a research background, right? So similar to perhaps as human, maybe if we have background knowledge, then can we write a paper which can be published in Nature Chemistry? The practical relevance is that it mirrors a real co-pilot setting where scientists supply a research question and optionally a brief survey of existing methods. Okay, so yeah, so maybe some idea about the existing methods you can optionally give to this particular agent, but otherwise just supply a research questions and then it generates the research idea hypothesis all by itself. Okay, so each collected paper, the paper decomposition, let's say a paper is retrieved almost the same way as I just showed the agent, that agentic code. So each collected paper is split into a structured component: background question, background survey, 1 to 3 inspiration paper titles with justification for each research hypothesis, experiments, reasoning process, right? That how the different stages of the experimental flow can be linked, and then summarization of inspiration. All components are described in natural language text, right? So no formal method here, just in informal way, natural language text, and this is where LLMs really excel. Okay, so strict versus non-strict background variants. Why two versions of background questions and survey? So one is this non-strict and the other one is strict. Rational is here. Without perhaps reading out this part, let's see the rational. So non-strict reflects experienced scientists, right, who provide comprehensive surveys and insightful questions. Something like, let's say, at the level of Bhatnagar Awadi, who would just throw an idea, right, with some insightful questions, and then of course these are like. Can we sort of land at moon, something like that, right? So these are like broad ideas, therefore it is non-strict. On the other hand, strict questions, it simulates scientists who are new to the research topic, so they actually try to explore a very sort of narrow focused topic, right? That's how we all do PhD, where we explore some narrow topic. So therefore two versions of background has been sort of utilized, experience level as well as the focus level. It encourages developing methods robust to varying levels of user experience. Okay, the reasoning process annotation. So the reasoning process, like I said, that your reasoning data is collected, right, in terms of how you arrive at certain stage of your thought process, right, and then you need to also annotate that data to train LLM. Okay, so example is background plus inspiration 1 plus inspiration 2 is hypothesis. Another example could be that background plus inspiration 1 or inspiration 2 plus hypothesis plus inspiration 3, that gives hypothesis. So all sorts of combination. So all of them, background, inspiration, all of them are just set of text, right? So they are strings, and then with those strings you can write Python code to sort of implement this reasoning process. Key observations: hypotheses may require multiple inspirations composed together. Some inspirations are interchangeable, right? So either you use this one, inspiration 1 or inspiration 2, then it is interchangeable. But otherwise, if it is composable, then it is sort of denoted by addition. So the reasoning chain is not always linear. Combinatorial associations are common in chemistry. You know it much better than me, right? The benchmark composition, we already said that 51 papers published after January 24 from Nature or Science, right? They also included, so in this equivalent category, they also included 13 papers in material science, polymer, organic, etc. And rest span diverse chemistry categories. So here is a sort of, the data from this benchmark creation. Okay. All right. So quality control process: after initial construction, domain experts verify each entry into 3 criteria: whether the identified inspirations are correct, does the background avoid leaking information from inspirations or the hypothesis? Information leaking is to address the problem that LLM should not just be using just be actually using which is already available, in the sense of generating new idea, right? So if it generates an idea which is already available, then it does not sort of shows its or shows to the to our sort of expectation that it can generate new idea, right? So therefore we should have this information leaking, that new ideas, let's say, which has been generated recently, so we should check LLM in terms of having its data to include the new ideas. So can the background plus identified inspirations logically lead to hypothesis? So by the way, all this is done by the domain experts, right? Domain experts. So here is the role of the scientific community in building the LLM agents, right? LLM agents also, although the engineering and technical part could be perhaps role of maybe a CS student, right? But domain experts actually have sort of leading role in sort of development of such agentic science, so to say. Okay, we already have spoken about this, right? That the LLM has never seen the ground truth hypothesis during training, and this temporal separation guarantees that any successful rediscovery reflects genuine reasoning capability, not memorization, right? Okay. The design philosophy modeled after the mathematical Olympiad type of questions, a small set of very difficult but meaningful questions. It is going into depth and difficulty, right? Not increasing the width to cover lots many areas. Contrast to the prior work, this benchmark actually targeted nature or science level chemistry, the hardest tier of scientific discovery. Of course, you are better you can better assess that claim than me, that chemistry, nature chemistry papers are hardest compared to, I don't know, JAX or Angichem or something like that. Okay, so here is the schema of this multi-agent framework. In this schema diagram, this little b denotes the background, right? So background knowledge is collected. So first of all, this big I is literature corpus from archive or other sources. We collected the literature corpus, right? And then it is decomposed into the background, right? And then the background are fed. Okay. H is hypothesis. Hypothesis will be so this background will be then mutated with inspiration. I denotes, this little I denotes inspiration. Background is mutated with inspiration, in the sense that it goes through mutation, refinement, and then recombine, and thereby we obtain the hypothesis. So a certain number of hypotheses will be obtained, and like we said, that these hypotheses are then ranked, right? Ranked. So let's say, thereby we obtain certain, refined hypothesis. And again, based on this, so I cap, this big I cap will be the one that we want to generate, the predicted, literature, so to say, right? And the background knowledge, this is the background knowledge supplied by, let's say, the expert scientist, right? This is the background knowledge obtained from the corpus, literature corpus, and thereby we obtain the hypothesis, and then it is ranked, and finally, so this is, like I said, that agent is also looping. So this will keep on iterating for a certain number of times, and finally we have our final result of generating the hypothesis. So yeah, so this hypothesis generation after ranking, let's say top K hypothesis will be obtained, and then the user will be supplied with one final answer. Okay, the claim is that a majority of chemistry hypotheses originate from a research background combined with one or more inspiration, supported by extensive discussions with chemistry researchers, grounded in cognitive science. We already said that key distinction from Swanson linking, that chemistry hypotheses typically require multiple inspirations. Background and inspiration need not be linked by intermediate papers. Applies broadly, not only to a narrow hypothesis type. just a little bit, I would say just a touch of mathematics here, because that would sort of make the task easier for me to explain what's happening formally. So we have the background, and then the inspiration. Hypothesis is essentially a function of the background of the background knowledge and the information gathered, right? The inspiration knowledge and the background knowledge. So B is the background knowledge, and I is the inspiration knowledge. Hypothesis, the generated hypothesis, is a function of that. Okay, where K is just a number. Typically, we take 1, 2, 3 such inspiration in chemistry, right? So we already said like several inspiration will be taken, but maybe 2 or 3, right? So given background knowledge, chemistry research is about searching for knowledge not known to be related to the background, but that can assist it. Associating background and search knowledge to compose a hypothesis. The search knowledge is termed inspiration. Okay, so here is this intractable probability computation. Given a certain background knowledge, what is the probability that we obtain the hypothesis? It can be decomposed into this sort of mathematical approach. That this is essentially I'll be just talking about So this is essentially a Markov decision process, right? So in my using process, what we do, that if you have like the jth step done in the process, then how to generate the j minus first process done, then how to generate the jth process. So let's say probability of coming up with this, I believe that it should be h, right? So there is little typo here. So it should be hj, given the background and certain j minus first hypothesis and the information corpus, right? So j goes from my mistake. So here is the hypothesis that given the j minus first hypothesis, right? The probability of coming up with the jth hypothesis, and given the j minus first hypothesis as well as the inspiration, the corpus and the background knowledge, what is the probability of coming up with the jth inspiration? So essentially, this probability of the hypothesis given the background knowledge, when we iterate it for k steps, it will be probability of the inspiration multiplied by probability of the hypothesis. Okay. So without perhaps going too deeper here, from LLM parlance, this probability is also called policy. This is policy probability, that what will be. So policy is sort of a name for that in terms of LLM training, and in particular, when it is inspiration, it is called policy. When it is hypothesis to hypothesis, translation, then it will be called transition. Okay. So in terms of language model training or large language model training, this is exactly the next token prediction idea. So at a very high level, let me explain it this way. You have certain, so LLMs, what do they do? You prompt it, right? And based on that prompt, it generates some response, right? So now that response, as we all have heard at some point or other, right? This is just next token prediction. So here what is happening, that we have background and we have our, inspiration collected. What is the next token prediction? So this probability is basically the language model's idea of next token prediction. So next token prediction in the sense that predict it both based on the hypothesis, both based on the background as well as the inspiration, right? And hypothesis will be refined one after another. So next token prediction expressed in formal way. So yeah, I'm not sure how difficult or easy it was to understand this part, but this is just LLM training way. Okay, so it's already 35 past. I will just skim through all of these details. I already spoke about this, right? That these two probabilities. And then the ranking formulation, development, that you have a number of inference results and then you rank it, right? So problem is that I is large, many I will be retrieved, many H generated, many hypotheses generated. Experimental verification is expensive, so we need to prioritize, right? So design a rating function the rating function should do something like this. So let H be the set of generated hypotheses. Then what is the probability? That probability of some ranked H, right? So let's say we have such n hypotheses generated, and what is the probability? So then based on the maximum probability, we finally output our result. Okay, so we already spoke about it. Multi-round pipeline. So like I said, that this will be looped, right? Any agent will be sort of working in loops, right? Several times back and forth, and that's what this one also does in multiple rounds. Default is 3 rounds per background, right? Each subsequent round searches new inspiration conditioned on the background knowledge and previous hypothesis, right? Number of I and H can expand exponentially across rounds, but yes, default could be 3 rounds. Okay, well, here is sort of key design choice without going into the detail here. Use LLMs, not citation graphs or semantic similarity, right? Many a time, what we do is that we just see the citation graph, collect some paper and see that how many citations that has gathered, and then based on that we tend to be tempted to take ideas from those papers which are like highly cited, right? It's like general inspiration, right? General, let's say, the tradition, if we could say so. But here it is, the idea is now sort of delegated to LLMs, right? So instead of just using citation and your personal choices, you rather use LLMs. It also perhaps will bring some unbiasedness. Many a time we get influenced by ideas generated by only the top or very well-known researchers, and we tend to ignore the ideas generated by not that well-known researchers. Here it is about LLMs. Okay, bold assumption is that advanced LLMs trained on vast scientific literature may already recognize novel knowledge pairs unknown to any scientist, right? And there is certain evidence that unsupervised word embeddings from 3.3 million material science abstract predicted functional materials years before their discovery. So this was a paper in 2019. Okay, evolutionary unit. Well, I think in the interest of time, it is already 39 past, right? So what I will do is that I will just go to the results here. Okay, just end-to-end recap of methodology. Assumption is that hypothesis is a function of background knowledge and inspiration which comes from the information gathered. Right? Decomposition, the probability of coming up with a certain hypothesis given the background knowledge is actually, if for K, let's say if you have sort of K different inspirations, then this is just a, and of course these inspirations are independent. So this is essentially the multiplication of those, the probability of the inspiration given, let's say the hypothesis generated up until here, right? And the hypothesis that will be generated given the previous hypothesis and background. And after that, ranking will be done on the hypothesis, right? The framework is a multi-agentic LLM system executing 3 rounds with beam search. Beam search, if you are coming across for the first time, just know that this is some kind of algorithm to do similarity search, how two ideas are similar, not just strings, but the ideas are similar. That is beam search. The ranked hypothesis ready for experimental follow-up. Once we have the hypothesis, then we can sort of take that to wet lab. Okay, and the insight is that by decomposing an intractable generative problem into tractable sub-problems, LLMs can approximate the scientific discovery process in chemistry. Okay, experimental setups, setting is Copilot in the wild mirrors real scientist uses. Copilot is like what we use these days as agents in our IDE, right? Input provided to framework, background question, background survey, chemistry corpus. Only the top 4% of inspiration or information is selected and used to develop hypothesis. GPT-4o was used, right? Training data cutoff was October 23. So then top match search, right? Highest, so top match score, the highest match score among all generated hypothesis from one background, right? And average matched score. So these are like evaluation metrics, which was sort of used to evaluate the results from this agent. Okay. Here is the matched score rubric, right? It should cover all the 3 key points, right? It covers 2 key points leveraged similarly to the ground truth, but does not cover more or all, right? It covers at least 1 key point, but used differently from ground truth, does not cover any key point. Based on that, different scores are given. Okay, and then baseline are from other domains, right? And then what they show is that the top score and average score here is better than other domains. Well, I mean, this is about the existing paper for this Mooj came paper, this particular agentic framework. So they are able to improve on the existing work by a substantial margin, right? Okay. Right. Okay. So final slide. Experimental takeaways. Evolutionary unit matters. So when these generated ideas are taken to experiments, it was found that the evolutionary unit matters. Mutation plus recombination yields 1.16 top match score over ablated variant. Right. Demonstrating that diverse association strategies are critical. Multi-step inspiration matters. Adding multi-step retrieval further improves top matching score. As it is seen here, right? And then expert validation, 41% of problems have at least one generated hypothesis covering at least 2 key innovations of a nature or science paper achieved with only 300 candidate papers and strict backgrounds. So that concludes my presentation, right? In summary, what I will say is that if you are still sort of thinking about using agentic workflow, then please, so see your area and think about using LLM agents for doing many things that perhaps in the last generation, by going by the last generation machine learning approach, you were doing just by regression, or maybe based on your intuition using some mathematical tools. And other LLMs have some reasoning capabilities which are yet to be discovered fully. No one understands at this point, however much we wish that we understand, right? But this is emerging as a very important tool for accelerating the scientific discovery. So that's all from my side. Thank you.
Thank you, sir. Any questions? Sir, I have one question. So these agentic AI systems are domain-specific systems like chemistry, economics, like that. So maybe how my area of interest might be very narrow. So that will get by the inspiration, right? For inspiration, maybe my work is very narrow. There might not be many papers to get. So in that papers also may not be from the nature science. So in that case, how accurate I can make a hypothesis?
Okay, right. So let me answer that. It depends on the LLM's capability. If you have a trillion parameter LLM, right, which has been trained on the entire internet data, your agent could be quite broad. It can at the same time cover entire material chemistry. Okay, but if you have like a small LLM, I don't know, 8 billion, the small language model, right, that you can run on your small workstation, you can be more focused. I don't know, organometallic could be like one sub area of
Yes, sir. Thank you. If there is any other doubt, it seems that there is no other questions. So thank you, sir. Thank you for introducing us the wonders of agentic AI. Thank you. Hello, sir. So there is no other queries.
Yes.
So thank you, sir. Thank you for the wonderful lecture. You can leave now.
Thank you.
section will be titled Drug-like property prediction of organics using physics-based, data-driven and quantum-inspired ML approach. To guide us, I'm very happy to introduce our next speaker, Dr. Arun Murugan. Dr. Arun Murugan is currently an associate professor in IIIT Delhi. He earned his PhD from Indian Institute of Science, Bangalore. After that, he worked across Europe and spent many years as professor at the KTH Royal Institute of Technology in Sweden. Please join me welcoming Dr. Arun Murugan, sir. Thank you for being here. Floor is yours.
So, like to speak here or here? Hello.
Yes.
Okay. It's on, right?
Yes, sir, it's on.
Okay. So you are able to hear me, right? Okay.
Louder, sir.
No, yeah, sure. Okay. Yes. The power is I need to connect. Okay, so very good morning to everyone. I hope you are able to hear me, right? Yeah, so maybe let me start. So what I'm going to talk about is that, so basically what I'm going to talk about is, which is very relevant for drug discovery projects, right? So many times, we are trying to optimize multiple properties in our drug discovery projects. Maybe, yeah. Right. So I'm going to talk about all these approaches. We also will see like what are the limitations or the advantages of using different approaches. Okay. So the tools are very general. You will learn a lot, and most of the results are coming from open source resources. You also should be able to do it by yourself later on. Okay. So this anyway, our friend had given very nice introduction about myself, so I'll skip this slide. So these are all the various topics that I'm going to cover today. So don't worry about it. I will finish it in time. So I will give very broad introduction to computational drug discovery and there what we are trying to do. And in fact, as I said, there are many things that we are trying to optimize. Drug discovery is a multi-objective optimization. So we will be optimizing multiple properties, right? So I'll be just showing some of the properties which are very important. and we'll be discussing like how we are going to compute these properties, right? So then in the end, I will be talking about something called de novo design. So we have developed some tool, LigGen, and we also benchmark it against currently available different tools. So that will be the the end. I will be talking about that. Okay. So actually, drug discovery itself is a very challenging area. Or in general, computational biology itself is a very challenging area because we are trying to solve some of the very difficult problems. For example, you take protein structure prediction, right? So there basically it is one of the most challenging problem, right? So the problem we are trying to solve there is that given a sequence, what is a 3D structure, that how it will fold, right? This is a problem that we are trying to address there, right? And that after 50 years, it was solved very recently. You might have heard about AlphaFold. The authors, some of the authors got Nobel Prize for building it, right? This is one of the problems that given the sequence, how to predict 3D structure. So there are many such problems in computational biology or computational material science, right? I'm just listing some of them here. So the one thing is like predicting structure of the peptide or protein, and the second one can be the crystal structure prediction. Given an organic molecule, which is the most stable polymorph that it can crystallize into. Okay, this is another important problem that very difficult to solve. Then in addition to that, polymorph prediction. For example, you take metformin. There are about some 50 different crystal structures available, right, in CSD, and many of them are co-crystallized with other co-formers, right? So it is one of the challenging problem. Like, what will be the most stable polymorphic form of a given molecule, right? Also, it is another challenging problem can be that whether a given peptide is it amyloid forming or not, right? So these are the few problems in basic science which are very challenging to predict. But when it comes to healthcare, then these are all the other challenging problems like binding affinity prediction, binding specificity prediction, then binding pose prediction. So I'm going to a little bit talk about all these topics, right? So, and you might remember that people conduct now and then different challenges, right? You might have heard about CASP one, that is prediction of the structure, of given a protein, right? So there are many challenges. What they do is they collect the experimental data, but then they don't disclose. Okay. Then they ask the researchers to try any tool, but then then you try to predict. Okay. In the end, they disclose the results, and then they show that which tool was doing better or not. So there are many such experiments conducted previous years. There was a experiment for predicting the permeability, partition coefficient, and binding pose prediction. These are so many challenging problems in computational biology, computer biology, right? So anyone wants to contribute there. Still there is it's an open problem. So you're welcome to do that. Okay. So when it comes to drug discovery, what we are trying to do, basically it is simple pair matching problem that we are trying to find a small molecule which will inhibit a given biomolecule, right? So these biomolecules are one which are apparently expressed in a disease condition, right? So we want to inhibit them using some small molecules. So you may think that it is a very easy problem, but the problem comes that the size of the chemical space we deal with is very huge, and then the size of the protein space we deal with is very huge. So for example, we have about some 23,000 genes, right, in our body, right? So some of the genes are apparently expressed in disease condition. So basically now you are supposed to design some small molecule which will inhibit this target protein, right? So basically you see the size of the hypothetical chemical space, it is about 10 power 60, and then this is GSK XXL, which is man-made chemical space, and its size is about 10 power 23. So, even to store all these chemical structures, we don't have enough space, storage, right? So this is a problem that now you have to find out the small molecule which will inhibit these targets, right? So when we are dealing with non-infectious diseases, the targets are very different, and when you are dealing with infectious diseases, the targets are very different. So in case of infectious diseases, rather the targets are from virus or bacteria, right? Probably you know all these things, okay? So the problem with drug discovery is that it takes, quite expensive. It's very expensive. Also, it takes quite a lot of time. So these are some of the projects which are quite expensive, right? Producing a Hollywood movie, aerospace exploration, right? Or building a nuclear bomb, right? And putting human in space. These are the most challenging problems currently, right? Very expensive projects, right? Drug discovery also at the same level. It involves about $3 billion cost. Also, it takes like 10 to 15 years, right? So, but you may think that then as a common man, how we can contribute to this? Can we contribute to the drug discovery project at all? So that's a question that I'm trying to ask here, right? But given that it is so expensive and very time demanding, only the big companies like Novartis, Pfizer, AstraZeneca, they can get involved in this project. That was the earlier trend. But nowadays, as thanks to the open source software development and then the algorithm development and then the computing that nowadays we can get easily, right? So thanks to that, now even common man get like some of like you or me like can get involved in the drug discovery. So the drug discovery is now democratized thanks to the open source software development where Sastri sir contributed a lot. Probably you know about MPTS, right? So he has developed a full workflow of drug development. The whole process is like free for you, but the only thing is you have to put your efforts, right? So he has contributed a lot. And we are also trying to do something there, right? So that's what I'm going to discuss today. As I said, drug design is a multivariable optimization problem where we are trying to simultaneously optimize multiple properties like binding affinity. So basically, it simply tells me how strongly a small molecule will bind to a given target molecule which is expressed in the disease condition, right? And there are other molecules. For example, your target can be in some of the organ, right? So your drug has to reach after you swallow it. It has to pass through many barriers. Your gut, it has to pass through the liver, it has to pass through the blood. Also, it has to go to the right organ, right? So there are so many barriers. People model it with some compartmentalization. So they assume that each body organ is a compartment, right? So it has to pass from one compartment to another one. Okay. So there are multiple properties. Control how the drug molecule which is taken orally goes to the specified organ. Okay, so we need to simultaneously optimize all these properties. So I mean there is a report that about 146 Alzheimer drugs developed. I mean many of them were failed. Right now we know that there is no drug for Alzheimer's to reverse the disease. Only for symptomatic treatments there are drugs available. So there are so many failures, and many of the cases can be attributed to that failure of optimization of the ADMET properties. Okay, even though the binding affinity was very good, but probably all other properties they were not optimized properly. Okay, so it is very important that we start looking into all these properties in the early stage of the drug development itself. Like you optimize all the properties simultaneously, so that in the clinical trials not many failures. Okay, so I mean. So there are earlier we used to do experimental high throughput screening, right? Where you take compounds and then screen, you take all the chemicals and then screen it using some assays, right? But then, the problem is that it was like usually trial and error based and it used to be very expensive, right? But now actually the same thing we are trying to use computational approaches, okay? So I'm going to talk about like what's the advantage. One advantage is that they are very cheap. Then actually, I mean, you can also screen large chemical libraries, and you can use less human. You can automate many of the processes, so you don't need so many human power, right? So these are all the advantages. But the problem is that how reliably we can predict many of these drug-like properties. So there we have issues, right? So we need to really develop very, reliable techniques to predict these drug-like properties. Then whatever we are doing screening using computational approaches should be leading to right compounds. Okay, so I'm talking about the accuracy here, which is very important. Let us assume that you have some scoring function, you have some software, but the problem is that are they working correctly? Are they predicting in the right way? So this is a very important question that we are trying to address here. Okay, so many times you may have many tools for screening compounds, but we are not sure that are they working properly, are they working for the right reason. All these things we don't know. So the addressing the reliability or accuracy of the scoring function is something very important. We are going to a little bit discuss about that. So there are very many approaches available in modeling any drug-like property, and probably you might hear about these physics-based models. So what physics-based models? Classical mechanics and quantum mechanics, right? So the classical mechanics tells me that if I know the phase space of a given system, I should be able to compute any property, right? Same way, quantum mechanics tells me that if I know the molecular wave function, I should be able to predict any property, right? So To solve this, I need to solve certain equations like Newton's equation of motion or Schrodinger equation to get the either phase or molecular wave function. Okay, so this is the ultimate thing I will be doing in the physics-based models. So in data-driven approaches, what I try to do is that, okay, I have a data set which relates molecules to certain property, right? In this case, maybe binding affinity or binding specificity or admit properties, right? So what I do is that then I try to represent this molecule in a meaningful features, right? Meaningful representation, mathematical numbers, numerical values. I need to convert these miles or molecules into numerical values. Then I have a data set which relates chemicals to some property, right? So I can use now this data set to build a reliable model. It's simply, you might have heard about linear regression, right? Fitting to some data, y equal to f of x, right? So same thing we are trying to do here. So you have a property which is y, and then you have chemicals which are converted into numerical data. So you have the variables x, right? So you should be able to build a relationship, okay? But the thing is that which are the descriptors that I need to use to build a reliable model, So there actually people have come up with many classical descriptors, and there are now tools available to compute all these descriptors, right? I mean 1D, 2D, 3D descriptors, also 4D descriptors. Then you also have molecular fingerprints, right? So all these things can be computed using different tools like Paddle, Moderate, or AudiKit. So then, in addition to that, you can also use experimental features like lipophilicity, right? Permeability, solubility, all these. We have a rich amount of data, which is coming from experiments. So in fact, you can use this data as the features, right? Then other thing is that you can do quantum mechanics calculation, and then you can compute various energetics or various surface properties or volume properties like polar surface area, molecular volume. Then you can use these features as the features for building a machine learning model. So the question is that which I should use? Should I use the experimental descriptors, or should I use the classical descriptors coming from the Paddle, Moderate, or should I use the descriptors coming from quantum mechanics calculations? In fact, you are free to use all the descriptors available. Actually, the model, when you are doing hyperparameter tuning, automatically the unimportant descriptors will be removed. Okay, so this is a paper where we showed that you can use all sorts of descriptors available, to you. So in fact, this paper, what we have done is we have used the classical descriptors coming from Paddle, then experimental macroscopic properties like refractive index, then absorption spectra, all those things. In addition to that, we also used quantum descriptors. So in this particular paper, we were rather addressing how to model power conversion efficiency, and we could rather come up with a very good model. You can see that R square is very good. But once we have built the model, then we also try to generate various molecules which are having better power conversion efficiency. Okay. So this paper is just to show you that you can use all descriptors available to you, and then later on you can also, the model will, you can try to remove unnecessary descriptors, so there is no problem at all. But this is like a property which is relevant in the material, energy science, right? Battery science. But here our concern is more about drug-like property, that we are interested in the properties which are relevant for drug discovery. Okay. So now the question is that how do I compute a drug-like property? I mentioned that we need to optimize multiple drug-like properties, right? But I always need to come up with the expression that how do I compute this property, right? I have a computer and I want to compute some drug-like properties. How do I do that in computer? That's the next question. Okay. So in physics-based model, any drug-like property can be computed as a free energy difference. And so this is a list I am showing here. You can see that inhibition constant or binding affinity, it is nothing but the free energy difference of a ligand in enzyme environment to water-like environment, right? Same way, your permeability is nothing but it's a free energy difference of a ligand in membrane to water-like environment. So the idea is that you can see that any drug-like property can be written in this form using this expression. So it is computable. In the end, I'm trying to say that any drug-like property is computable. So once you know how to compute it, then you can basically just do these calculations and then predict it, right? So you can see that there is a very good relationship relating permeability to delta G transfer, which is nothing but free energy of the ligand for going from water-like environment to octanol-like environment, right? So once you have the delta G transfer, you should be able to compute the permeability. So there are so many different approaches for computing binding affinity. I'm just telling you that, I mean, this is just to illustrate to you that there are so many tools available to predict binding affinity, and their accuracy varies, you know, I mean, depending upon what type of we are approaching, which approach we are using, their accuracy changes, right? So you can change, you can see that there are so many range of different tools. So the most very fast one and then less accurate can be the molecular docking softwares, like you might have heard about Autodoc, Vina, right? So then comes this molecular dynamics and free energy calculations. Then we have hybrid QM molecular dynamics. Then, you know, more accurate QM fragmentation scheme. So this slide is just to show you that there are so many tools available for computing the binding affinity itself. Okay. And a simple scoring function is shown you here, you know, which is implemented in Autodoc. You can see that the protein ligand docking energy is nothing but sum of protein ligand van der Waals interaction, protein ligand electrostatic interaction, and then protein ligand hydrogen bond interaction. Then you have something coming from the solvation, like the number of rotatable bonds in a molecule. So that contributes to entropy contribution to the free energy. Then this, I mean, we can ignore it is coming from that when the ligand in the vacuum condition, when it goes into the protein binding site, there is a conformational change that contributes to some internal energy change, that also we are accounting for in this expression. Okay, so this is a simple docking energy implemented in Autodoc. And then you can see that you know, in if you see Glide, there is a slightly different implementation which also account for you know, metal protein interaction or metal ligand interaction. But anyway, we don't need to go into the detail, just to give you a feeling that what you're docking energy, like which is proportional to the binding affinity, right? So one can also use more sophisticated techniques like quantum mechanical fragmentation scheme. But the issue is that these techniques, quantum mechanical techniques, are very expensive. Their time complexity is n power 3 to n power 7, where n is the 1 electron wave function. So if you see nitrogen molecule, we have already 14 electrons, right? So if you see, if you want to do like coupled cluster, then it goes like 14 power 7. You see, then it is, then you cannot even think about protein and you know, ligand complex systems, right? Of course, sir, in the earlier time in Pondicherry, he did a lot of QM calculations, but now he moved out to do different things. But it is very expensive. You know, in this field, people knows that using quantum mechanics for drug discovery is not that easy. So we have come up with some simplified approaches, which is called quantum mechanical fragmentation scheme. So what you do is you fragment the whole protein into individual amino acids, and then you compute the interaction as the sum over amino acid ligand interactions. But in the end, of course, when you are cutting across this peptide bond, you are you know, making some approximations. So you need to account for such effect also. But the advantage is that, I mean, it is more reliable, even though computationally very demanding. So in some cases where the you know, binding specificity is very important to model, you will have to rely on such techniques. Okay. So now that was a physics-based model for drug-like property prediction, right? Now I'm just telling you like how to go about modeling the drug-like property using a machine learning model. So what do we have here? So you have a data set which relates the chemical structure to some property. It can be binding affinity. Here what we have is simply a PIC50, right? It is a negative log of IC50. So what you need to do, then basically you convert these smiles into some numerical data, right? So basically what you do is there are multiple steps involved. Convert these smiles into mole2, then you compute various descriptors like 1D, 2D, 3D, 4D descriptors, also fingerprints. Then you also need to do some data cleaning, because when you get the data from Hempel database, maybe in some case some of the data missing, right? So you need to correct that, and then you need to do the feature selection, right? Then you do the training, and then you also need to do something like hyperparameter tuning. Then you build a model. Okay, so model, now you show that you can see here how this actual PIC50 when compared to the predicted one. Okay, you can see that. So there are certain metrics to show that how well the developed model is functioning. So there are metrics like precision, accuracy, or in this case it is a regression model, right? So we have something like R square. Then you can also compute root mean square error, mean average error. So all these metrics are there. So this is how we build a machine learning model to predict the drug-like property, right? So now I will show you some example where we tried physics-based models and then machine learning model to predict binding affinity. And then in this case we have taken the MUOB target, and that's what shown in the right. So here our aim was to predict the PIC50. And we used physics-based model like using Autodoc, Vina, and then we also tried MD free energy calculation based up. So you can see that none of these methods are giving correct results. There is no correlation between predicted and experimental value, right? So this means in this case the physics-based models completely failed, correct? Then we tried with simple machine learning model using some 154 molecular descriptors computed using paddle software, and in this case you can see that the model performance was fairly very good, okay? And in particular the C, which is multilinear, I mean perceptron, MLP was doing very good. So this is just to show you that machine learning models are very good in predicting binding affinity for MAOB when compared to the physics-based model. So in this case, now I am going to show you some output that in this case what we are trying to do is that we are trying to predict the binding pose. So what do I mean by that? So we have the experimental binding pose, right? So people have crystallized protein ligand complex structures and then they are available in protein data bank, right? So now let us say that I use some software to do the same thing. I remove the ligand and then I do the redocking, right? And then the complex structure I get, is it very similar to the experimental one? So this is the question I'm trying to ask here, okay? So you can see here, I mean I have overlapped both experimental XRD structure with a predicted one. And this is the monoamine oxidase B again, and FAD is the cofactor and sulfonamide is the inhibitor, okay? So you can see that there is a very good match between the experimental sulfonamide structure and then predicted sulfonamide structure. Okay, so I mean in the end, I mean this tail part there is some issues, but otherwise you can see that there is a fairly very good prediction of the structure. Okay, so I mean you can use two metrics, right? When it comes to the binding pose prediction, we use these two metrics. One is the RMSD between the experimental structure, experimental binding pose, and then the predicted binding pose. So usually they use a criteria called 2 Armstrong. If it is less than 2 Armstrong, this RMSD, then you can say that you have fairly well reproduced the experimental structure. Okay. So when we are doing the prediction of binding poses, usually we get like 10-20 different binding poses. Okay. So usually the top one is the one with the best binding affinity. So you can compute RMSD between that and then the experimental structure and report it as a metric. And you can also do one more thing: take any of these binding poses predicted and then compare with the experimental binding pose and report it whether your structure was reproduced. Okay. So in fact we are using both these metrics to compare the performance of the molecular docking softwares. So what we found was that in this case we have taken kinase, and this work was published in recently in RSC Advances. So what we found was that deep learning method GNINA was very good in predicting the binding pose when compared to physics-based methods like Vina, Doc6 or Autodoc 4. Okay. So that's the take-home message. And then that was for the all-atom RMSD, and this is for the center of mass RMSD. Okay. When we are using center of mass RMSD, most of the physics-based softwares are also doing reasonably well, very good prediction. Okay. So this is another example. I mean, in the previous case, what we have done is we have simply removed the ligand and then just redocked it. Okay. That means we retained the ligand conformation as it was in the experiment. But then when we submitted this particular paper, this was on base 1 binding pose prediction. The reviewers asked, but you are doing redocking. If you do cross docking, what type of results you are getting? So cross docking in the sense, you build the ligand from the scratch. Like you start with a smile and build the ligand 3D conformation, right? And then do the docking. So this is called cross docking. So in fact, in this particular work, we also did redocking along with cross docking. Okay. So I am going to show you some results. So in this case, we tried 3 different physics-based approaches and then deep learning approaches. You may see that you might have come across AlphaFold 3, Fold, Boltz 2, DiffDoc. They all work with different principles. They all are deep learning methods, but some of them are diffusion-based. Some of them are trained on different PDB databases, right? So and again here also we did the metrics. We used the metrics all atom RMSD and then center of mass RMSD. Okay, and I am going to show you the results. So this is and in this particular case we have results for 2 targets. Above form, also hollow form, right? What you see here? What you see here is that AlphaFold and DiffDoc and Boltz. These are all the recent deep learning approaches for predicting 3D structures. they are doing really good, right? I mean, when compared to physics-based methods. And independent of what type of target we are using, is Debo form or hollow form, you can see that the physics-based models are doing really good when compared to physics-based models, okay? But when we are doing the redocking, that means we are using the same geometry as it is in the experimental structure and then do the docking. You can see that even physics-based models are results are improving, and you can see that the even dock 6 autodock also giving comparably good results. Okay, so I mean, in this case, we also tried, flexible body simulation, flexible body docking. So by that, what we mean is that usually when you are doing docking, right, your protein is fixed. I mean, there is no geometrical change allowed in the protein itself. But then certain softwares like Autodock, Vina, they allow that you can include some flexibility for the side chain residues in the binding site. Okay. So when we did this flexible docking also, we didn't see any improvement, but rather we saw that the performance was rather getting worse, and we were trying to explain that. So what we are showing here is that when you are including the when you are doing flexible docking, and you compute the molecular volume or binding site volume, how the distribution looks like. So the broader one, you can see that is the one, the experimental PDB structures binding site volume. Okay, you can see that covers a bigger range, wider range, right? But when we are using flexible residue approximation, the volume range is not so big. You can see that it's only a smaller range is covered by the different softwares. So we are proposing that this can be a reason why these flexible docking approaches fail, when compared to the rigid body approaches. Okay, because the volume change, volume distribution in experimental cases are very wider. Okay. And then now I will go into some discussion of this log P prediction. As I said, this is another important property. So basically, when you take a drug, it needs, let us say, there are some intracellular targets. Then they need to go into the cell to act on the biological targets, right? So that is dictated by this property called log P, okay, which is proportional to permeability. Okay. So here, what we tried to do was that we wanted to use some quantum descriptors, coming from quantum mechanical calculation. So we want to see that quantum descriptor based model, how well it is performing when compared to classical one. And this work was jointly done with Professor Sastry. Anyway, we have submitted this paper and it is under review. So here what we have done is, we have used, we tried 3 different models. One is graph theory based model. So where we represent molecule as a molecular graph, and then the atom properties goes as node properties, and then the bond properties goes as edge properties in this model. Then we use the second model, which is outer like environment. Okay, so we also include the delta G. Okay, so one important reason also we are include this polar surface area, and people have related this polar surface area to permeability. In many cases, they say that when the PSA is larger than 140 Armstrong square, their permeability, membrane permeability is good. Okay, and then you can see these are the other other values recommended for PSA to have better permeability in the blood-brain barrier, or placenta permeability, it should be larger than 60. So these are like coming from the experimental report. So this is the reason why we also included the polar surface area in our machine learning model. So this is the output of the our research. So here what we are showing is that the first one is the graph theory based GNN model. That's a superiorly performing with the R square 0.96. Then comes a hybrid model where we are using classical descriptor as well as the quantum descriptors. But you can see the number of descriptors are really too many, 1857 descriptors. Okay, so that is the next best one. Then the third one is moderate descriptor based model. Then the physics based model, it is the fourth performer. But the advantage is that here we are using only 31 descriptors when compared to, you see, that 1800 descriptors in the purely classical descriptor based model. So as you can see here, the purely quantum descriptive model is not doing very good. But I mean, with the minimal number of descriptors, the performance is very good. Okay, so that's a take-home message here. And this is just a predicted and experimental log p values using different methods. Then in the hybrid model, you can see that the top important property which is contributing to the model performance is delta G. You can see that which is as expected. Delta G contributes to the performance of the model. Then we have also the polar surface, non-polar surface area. That comes as the 8th descriptor. So we can see that which are the descriptors contributing to the model performance, right? So we try to understand that why the quantum mechanical descriptors are not doing well. So we know that we use the approximation that when we build the quantum mechanical descriptor due to the limitation of the computing, we didn't do the full optimization. Okay, we did single point calculation in 2 different solvents, which is a problem. Okay, so which is the reason why we are seeing that this quantum mechanical descriptor model is doing not very good. So we try to understand that. You can see that this is the error with increasing number of rotatable bonds. But that means when the molecular flexibility is larger or number of rotatable bonds are larger, then basically the average error increases, which means that to some extent we need to optimize the geometry in the solvent. I mean, which we will be looking into. We'll be looking into this aspect in another project. But this is just to show you that where the error is coming from in the quantum mechanical descriptor based model. Okay, I mean I should wind up in another 5 minutes, I guess. So what I will do is that I will skip this project where we also try to build quantum mechanical descriptor model and the classical descriptor based model. So the problem here is that we try to use the SwissAdmin, which is online tool, online server to predicting the log, blood-brain barrier permeability. Okay, and we found that in many cases it it failed. I mean, you can see that out of 7,700 compounds, it was giving results only for 6,500. In addition to that, there were many, only 60% accuracy was shown for many of the molecules. I mean 60% accuracy was shown. Okay, so we thought that the SwissAdmin is not doing well, so we need to build a reliable model. So in fact, we were working on it. I will skip that project results. Rather, I will go into the final topic. So in this one, what we are trying to do is that, so we are using a generative AI based approach to build a to design new molecules. So basically, you might have heard about de novo design. When you want to come up with a new molecule, right? What you do is there are 2 approaches. One is start with a chemical library and then screen against your target. That's one approach, right? The second one is to build the molecule using de novo approach. That means you take different fragments or atom by atom, you try to build a molecule which will bind to the binding site in an efficient way. Okay. So here, I mean, there are already tools like Link Builder and then Pocket to Mold, and then there is Reinvent 4. These are the tools which are already doing this de novo design. But what we thought was that we came up with some new idea that instead of taking the fragment from the from the file, why don't you generate on the fly? Okay. So what we did was that we used it as generative AI, which was trained on Hemble, but then fine-tuned on the Link Builder fragment library. Then we were using that to on the fly get the fragment. Then we were assembling the fragments to build a new molecule. Okay. So the one difference in LinkGen is that we are generating the fragments on the fly. That's one difference. Okay. And then we benchmarked it against various tools available, as I said, like the Pocket to Mold, then Link Builder, then Reinvent. So we tried 3 different targets. You can see that the LinkGen is giving compounds with better binding affinity in all 3 cases, right? So we tried the base 1, monoaminoxidase B, acetylcholine esterase, and then the right side what you see is the known inhibitors for all these targets. So the compounds we are getting is better than the known one, also those generated by the other tools. Okay, that's one thing. Then the second thing is the generated compounds, how novel they are. This is very important, right? For example, you generate a compound and if it is already in the library, then it is of no use, right? So you always need to check against the novelty metrics, right? So that also we have done. So you can see that our compounds the component generator from LickGen, they are having very good, I mean, novelty. That means the novel, when the score is 0, it means that the components you generated are very similar to those in the library, okay. But if they are close to 1, it means that the components generated are novel, okay. So you can see that fairly good novelty is seen by the component generated from our approaches. Then the third aspect is that the synthesizability. I mean, let us say you design some compound, hypothetical compound, but can you, if you cannot synthesize them, then it is a problem, right? So you also need to check the synthesizability. So we also computed synthesizability, and then you can see the larger the value, then it means that they are easily synthesizable, okay. And you can see that LickGen generated compounds are, I mean, easily synthesizable. That's so we evaluated against docking energy, we evaluated against synthesizability, we evaluated against the novelty. So this means our LickGen is doing a good job when it comes to these 3 targets. Then we also benchmarked against this gross docker data set, and these are all different benchmark criteria that we were using. And you can see that LickGen has, in average, it generates compounds which are having high binding affinity. So this paper is already, it is about to come online in scientific reports. So I think that's about the de novo design, okay. So basically what I'm trying to do is that, I mean, so the drug-like properties are computable. So you can build a reliable model so that, you know, you can screen compounds very easily using computational approach. That's one information I want to pass you here. Also the quantum mechanical approaches, even though more expensive, sometimes it doesn't lead to a better model when compared to the classical descriptor based model. But one thing is that it is giving an explanation, like why some model works. I mean, we can get insight. The explainability can be very well obtained from the quantum mechanical descriptor based model. So that's something very important, okay. So with that, I mean, I will close this lecture. I mean, first I need to thank Professor Sastry. I mean, he's a mentor for me, and then we also collaborate in a lot of projects. So thanks to you, and then for the organizers, so, and then my students, you know, who is involved in that. So if you have any questions, you can ask. Thank you very much. Yes. Hmm. Right, correct.
Usually, is it not easy to identify when features maybe blood
I mean, so here we use all possible quantum mechanical descriptors, right? And many of them are based on they can be computed from the frontier orbital energies, HOMO, LUMO, right? I mean, so along with that, we are also using like the non-polar surface area, then you know, volume, all these other descriptors, also the solvation energy. So what we are finding is that the polar surface area, solvation energy, these are the most relevant descriptors contributing to the performance of the model. Yes. Did I answer your question correctly? Yes. Okay. Yes.
Here, computational time for doing quantum critical calculations will take at least 100 or 500 times more than the
Definitely, sir.
other classical mechanical descriptors.
Yes. That is
But
true.
your work clearly show that the classical mechanical descriptors are better than the quantum mechanical.
Yes, in this particular case.
It shows that when somebody is using the first principles calculations, they need not get the better results because the type of approximations that you have in the quantum mechanical calculations are much higher. So more computational time need not result in better results and better correlations in drug discovery.
Correct, sir.
So this is something which is very important to realize.
Yes, sir.
So the impact of AIML, the diffusion-based methods and other methods are going to play a much more important role, and they are slowly going to replace some of the highly computationally demanding methods.
Yes, sir.
I don't know, but how about MD simulations, the time evolution of the protein structure? Will that also have an impact with the first principles calculations versus the AIML?
Yes. Yeah, so in this case, we have benchmarked the binding post prediction, which is related to structure prediction, right? So basically, what we are trying to do is the 3D structure prediction of the protein ligand complex structure. So what we are seeing here is that, many deep learning methods like DeepDoc, Bolts2, then AlphaFold 3, they are really doing very good when we are doing cross docking. That means you completely change the, start from the smile, the presentation, and then again do the docking. So they are doing very good when compared to physics-based models. But physics-based models, they are doing good when you already start with the geometry which is seen in experiment. So
Very unconventional thing that you have found is
yes,
the flexible docking is
yes,
giving worse results than rigid docking.
yes, and that explanation is yes, sir. That reason is here. So in the if you, yeah, one reason is that what we are showing here, we are showing the volume distribution, right? So we took like 420 PDP structures of base one, and then we estimated the volume, and then we have shown the distribution. So when we do the flexible docking, this whole range of volume is not covered. So flexible docking only account for small volume change when So because the reason is that it still assumes the backbone atoms fixed. Only the side chain atoms are allowed to move. So because of that, the volume change cannot be fully accounted for. So that can be one reason that why the flexible docking approaches are failing. Yes.
When you're doing flexible docking, you are really allowing the large surface space. When you're doing rigid docking, you are already close to the final close which you are trying to reproduce.
Yes.
So that is probably the artifact introduced because targets are already close to the what you achieve in the end. Flexible, you are allowing them to be distorted.
Yeah.
So they will perhaps go to another local minima and not.
Correct. Yes.
So it is, I think, to some extent expected. Unless your initial pose is very close to your, you will not be able to.
Correct. Yeah. That's why we see that the redocking approach, when we are doing redocking, then even many of the physics-based methods are doing very good. So because we are already starting with the geometry of the molecule, then we are just still placing it, and then it seems to be working. But for when you are doing cross-docking, you can see that the physics-based models are failing. Then in that case, only the new methods like AlphaFold 3, Bolts2, DiffDoc, they are doing good. Yeah.
It's like somebody asked to find their home. If the person is left too far away from his home, it
Right,
will
sir.
be difficult to find.
Yes.
But if he is nearby, he will be able to find.
Correct. Exactly. It's the same. Yes.
From a historical perspective, if you look at a lot of which particular method has taken a lot of computational time, is a molecular dynamics.
Yes.
Even the IBM Blue Gene and this David Shaw, they have run these calculations for 2 years.
Yes.
As a thing that how the ligand will look at go to the its natural binding site. But these methods, especially the overwhelming success of AlphaFold, is neither accepted nor expected nor acceptable because as we were looking at, if you are coming close to the location, if GPS location is very close to your home, there is no point in trying to further optimize this. So this message will actually tell us the limitations of many of these first principles calculations, where you do it without limits, without really putting some restrictions.
Yes.
So this may be very interesting.
Yes, sir.
See that how AIML will integrate the conventional first principles based molecular simulations.
Yeah, so one problem with, still why we need a quantum mechanical approach is that there are many cases where the, classical descriptor based model may not work. For example, let us say there is a metal atom something, then the software will fail. They will say there is a metal atom, it will fail, right? But then still the quantum mechanics based approach you can still use. You can compute the descriptor and then build the model. So that's another advantage.
I was seeing that one model of the GCA, that convolutional network, why the big challenge of that long range dependence?
Okay.
Because if you use the software, that will be to the auto tuning by that long term dependency and also the orientation. Because when we think about the relation of the bonding, how much depth it will going, it's a big challenge of that make optimize. So in your program, because that's also take a huge computing, also takes times. So how you are optimizing? This is that your manual tuning or auto tuning by the software? Because that's a big challenge because you are showing the transfer value is coming at 0.9 something and it's very good. Good. So that's why I'm asking that. Because manually, what's happening many times, you are you know that property of the salt molecule. So
Right.
depending on how long it will go, you can understand. When we give this your in models, so what do you think is it one of the big challenge? So is it done by the manually or is it auto by this model of the software? What are you using?
Okay, in some cases, I mean, we use the default parameters, right? But sometimes, I mean, if the performance is not good, then we try to increase number of hidden layers. We also try to do that because many of our students are from computer science background, in my group. So then basically they can even, play around with these parameters to get a better model. They usually they do that, yeah.
Because normally,
Yes.
unique, normally other neural network and graph neural network is challenging.
Okay.
It's totally unstructured. And that in the tuning that optimize of the copper takes
Right.
a lot of time and also
Okay.
if you have that if you give us your concept of that, how depth it will be going or also the orientations.
Correct.
Will you convert more
I mean, you are asking very important question. See, when we are referencing a graph as a molecule as a graph, right? We are only passing topological connectivities.
Yes.
That means only 2D structure is there, right? But it is performing better than one where we are also passing 3D descriptors. Like for example, the hybrid model, we have 1D, 2D, 3D descriptors also, right? So, but we were surprised that why then, the graph neural network model is doing good. So we really cannot figure out the explanation. We are thinking that it somehow captures the substructures which are essential for the properties, right? So probably that is the reason why it is performing good. But it's a surprise to us. Maybe we need to understand a lot. Yes, but that's a good question. Yeah. Okay. So I mean, if there are no other questions, I mean, I can stop here. Thank you very much.
Professor Surya, Professor Raja, Professor Madhavi, Professor Arul Murugan, and Professor Shandar Ahmad to be the panelists. Come in the middle, come in the middle. Yeah, please. Come in the... Good afternoon, friends, and it's a 3-day event. Being a midsummer, lots of the participants have decided that they had enough till lunchtime. But there are still some very enthusiastic people remaining here. So we would like you people to have some sort of an engaging, interactive panel discussion. And the theme is the impact of AI on Indian healthcare. And I request each panelist to introduce themselves and then give their few thoughts that they have. And I request Dr. Srijit to talk about the impact of AI in Indian healthcare, especially from the large language models and foundation models perspective, because he's an expert in that area, and I would like him to, yeah. Maybe we can start with the question. Yeah, we can introduce and then, because as a co-organizer, you can pitch in.
Yeah, hello. Yeah, thank you for coming for this workshop, and I hope you enjoyed the sessions in last 3 days. And yeah, I think we'll have this panel discussion, which is also going to give you a lot more insights into the AI and its use in healthcare. Yeah, myself, I'm Dr. Sridhar. I'm a faculty from Computer Science and Engineering Department, also associated with Department of AI at IIT Hyderabad. Yeah, so I'm actually not a researcher in the area of healthcare. I just work in general on artificial intelligence, on different learning problems, continual learning, causal inference, multimodal learning, Bayesian learning, uncertainty modeling, etc. But of course, using these techniques for different deep learning models and problems in artificial intelligence, natural language processing, vision, etc. Yeah, so I see that there's a huge interest in the field of healthcare and using AI to solve several problems in healthcare. And I have seen several startups who are actively working on solving problems in AI for healthcare, and several faculties across several institutes in India. So I think it's a very great time for healthcare, and there are so much participation across the entire nation in trying to solve several problems in healthcare. But I also see some kind of a disconnect between the practitioners in the research scientists working in that specific domain, let's say in computational biology or some material science or any biology domain, where there is some kind of a disconnect in the way they are not using AI to its full potential. Recently I had an interaction with a researcher working in computational biology. Apparently they are still following the practice of searching internet to find out relevant literature and going through these papers to figure out the specific information they need without using any new AI techniques, AI tools, let's say even ChatGPT. And they were surprised to see the kind of results these AI tools can provide to them, and in helping in gathering the right information, improving their efficiency, productivity, etc. And this is something I also see, okay, even though there is a lot of interest, there is still some kind of a disconnect between how AI tools are used by specific practitioners and researchers working in healthcare, and we may need more such workshops and more such programs to make them aware of the AI techniques that is available out there, which can help them to improve their process of whatever research problems they are solving, and maybe like drug discovery or any other problems in healthcare. So this is just a brief observation from my part as an outsider, but maybe other panels can give more insights about how they see AI.
Thank you. I request Professor Mahathir Raja, and we all know that the graph neural networks and artificial neural networks, convolutional neural networks, reinforced neural networks have been emerging as much more powerful tools. As somebody who is leading an academic institute, I would like him to talk about the relevance of learning these things and teaching them at a university level, and how this has transformed in the last few years, and how it is going to be there in the next 5 years. He's free to talk about, but I think if you are able to talk, that will be nice.
First, I'd like to give thanks to Shastri sir to really get a great opportunity for me to be in the panelist, as a panelist. So I'm an academician and I love that mathematics. My background is mathematics. But I have a curiosity. Normally, mathematics means what we understand, dealing with a number. But normally, childhood, we do the number. But when people think about the mathematics, they use the relation between the number. Because when you think about the analysis, real analysis, function analysis, algebra, they talked about the relation. So they don't deal with the number, they talked about the function and behavior of the function. So mainly mathematics, always they're trying to capture of the function and the pattern. Now, my basic research domain also till so far my PhD in that fluid mechanics. Then as my postdoc is also the Germany is doing that turbulence, that modeling. So where that normally engineer and physicists they're working, where they're failure, and turbulence characteristic is a very unpredictable, uncertainty is there to how the mathematics they can capture it. So I got a really very good intuition during my postdoc. Then coming back also, I rigorously do the mathematics and use the mathematics for the different application. Now I talked about that today. That theme was that AI in that healthcare or drug discovery or any health related that domain industry. So when we talked about that AI normally we are talking about the artificial intelligence. So until now, question is coming that human beings are intelligent. So what is intelligent? That is really very difficult to perception. But in a mathematics we can define it very nicely. We can define what is intelligent. And artificial means that intelligence we give that intelligence to the machine and machine will work, behave like a human. Now, when we talked about that neural network is coming, and that Sir already given the very beautiful presentation of the in that morning, that how that intelligence and how is that first neural network concept is coming. So normally you see that we see that biological neurons, how they work, analogy making and mathematical model they establish. Now, if we think about that, we try to establish the relation of the mathematical structure. So we represent, there is a X and Y, there is a regression problem or classification problems. So X and Y is there. We try to define a function. So and function that represent by the neural network. So when we talked about the neural network basically is nothing but it is a composition of the function. So it is not a simple function. So we remember that is a complex function and composition function. These two things concept is a mathematically is different. So normally when people do the work of that any other than the mathematician, that any engineer or any science people use the neural network, they draw the diagram, the graphical diagrams, and they do that connectivity, and they try to train the models, and their thinking is that, yes, I am training, there is a number of the parameters are there, the parameters will be trained and will be estimated value with that our existence data, and it will be fit to reduce that your optimization problem. But mathematically, if we think about that, then we understand that it's a composition function, the behavior of the function. And nobody knows about exactly what will be the function. So now, normally, when we talked about the neural network, this is one pattern of the mathematicals. When we talked about the CNN, CNN is also the graph approach. So it is a structure. When the CNN is one kind of the graphical structure, or the one kind of the mathematical composition function is given. When he talked about the language model, the data, because I was telling that normally mathematics deal with the relation among the numbers. So whether it's a language model or you put a biological any problem, so when you try to capture with the data some information, that means we try to capture about that relation about that data or numbers. So then you think the language model we talked, the language model is very interesting characteristic, the sequential. And when the biology is coming, they are talking about that genomes or gene pattern. So there is a thinking about the sequence. So Sar was writing very one slide, it's very interesting that it is sequence, then is writing the structure, then it is writing the function. Now there is three terms are there. Normally when we define what is a sequence, then you have to tell about the structure, because normally structure term, if we tell normal language, we always use it. But structure to define in mathematics, then you have to tell that there is a sequence. That's why it is called that structure. Then when you take that, what is a sequence? Sequence means there is a function from that, or natural number to that, or real number or anything. So it's a very beautiful one relation of that mathematical concept. Now ultimately, that when that any biology or any other domain, engineer domain, they try to do something. So they try to make that relation. Now, when it is a sequential is coming, then sequential pattern and neural network, probably CNN or DNN or ANN, that pattern will not work very nicely, because mostly the data, any data, they have some distribution. Because normally if you think about that, any data analysis, then we go back the backside of that statistics. So we think about the statistic, then it's coming that distribution. When you talk about the distribution, then it is coming that is a population. What is the population? What is the distribution they follow? And then again it is coming, the population is always unknown. When a statistical data has some characteristic is there. So that we think about that population distribution or the statistical distribution. So with the help of the statistical distribution, we try to make that our population estimation. That is the concept mainly. So normally when we do any neural network also, we assume a hypothesis. And that hypothesis, with that value of the data, we do the testing. That is the main concept of the statistics is coming to the estimation of the population. Ultimately, end of the day, that our population, that is unknown totally, and is the uncertainty more, that try to get some information. And that's why when we talked about that CNN, ANN, DNN, when we were talking, then sequential data, if you put that, normally the data, among them data, what is the relation is that will destroy if there is a sequence. Then you need to go to the RNN. So when you talk to the RNN, then it is okay, time series data, language model data, then genome data, that is very nicely they're working the RNN models. RNN, different type of the models are coming. Then people started talking about that in that 2017 or sometime, that their paper is coming, the attention mechanisms, and they're making the transformer. So attention mechanism transformer is the long-term, short-term memory. That is a very beautiful concept. I'm not going to details. And next, this is a 2000 or that time, that is coming up the graph neural network. The most important also the drug discovery, the chemical bonding reactions, or the biological reactions, which is that described by the graph. And the graph is a very, very most complicated structure, because it is unstructured. Till so far, if you think about the ANN, DNN, there is a structure network, a graph network. And that a function, composition, it is a structure. And the graph neural network is totally unstructured. Because we don't know that what is the depth will be the relation dependency, that is the things are there. So normally when we study of that we think about that how the mathematics are there, because if we use as a researcher, if we use a software, then we are not bothered about that, how it works. Just use a software and that my accuracy value is coming on optimization and doing it. But if you think your domain knowledge is very good. If you are a biologist, means if you have a very biology good sense is there. So if you understand that biological behavior, or if you drug discovery, if you think about the chemical, if you understand that the physics between that, then you can make a more better design of the algorithms, which will work more efficiently, better actually. And that is that only the learning of that, when the researchers are learning, so when the learning of that AI, they should be concentrated that part. Another part also, sir was discussing of that, interpretable of that your model. So nowadays, people are working on the deep learning, where it behaves like a black box. So you trained and you understand that result is okay, you are happy or something, some accuracy level. Now there is another challenging is coming, that whether how you reach your decision, how will you explain, what is the logic behind it. So if you think about that AI, the first, it is coming that logic. So it is because first AI also, Turing was giving that some very intuition that is a proposition, a mathematical proposition, proof, how to reach your proof that is correct. So now the explainable AI is also coming, that is a very big challenge, and particularly explainable AI is very relevant of that healthcare. So doctor is telling something, but doctor, how they are reaching the decision. Because abroad, I have seen that, abroad, particularly most of the people are spending a lot of time in the abroad, and in India doctor, they don't have the more time. Abroad, particularly the patient that speak, they give time, they explain. India doctor, most of the doctors, if you are going, you are telling your symptom and they are prescribing. You have the curiosity actually what is happening, whether really required to take the medicine or what is this. And nowadays also people know that you don't give the prescribe anything, first you explain that what is happening. And that's a very big challenge, that the doctor doesn't have the most time also. Now how the AI can help that place. And another times also you see that I have observed that also, I was a little bit working of the few project also, that when patients are going to the doctor, they are speaking, they are telling the symptom. And when that half portion they are telling, and the doctor started to write that prescription. So the question is coming there, that whether doctor is listening everything, or after listening they will write it. But they don't have the much time. And whether they are correcting all points. Now the AI tools also, they can help you. Suppose, and they are speaking their own language, the multilingual is large language models. They speak their own language where they feel comfortable. And automatically that will be recorded in a data. And from the data, the doctor can get some idea. And then doctor has their own intelligence to do it. And also there will be explainable things when patient is coming, and their prescription, explanation. So many models can be done. So that's why that here the AI can help different aspect. And as a academician, I will always tell that to understand the total architecture and understand the domain knowledge, understand the physics of the problems, then use that AI model will better that a better result. So thank you.
So now I request Professor Suresh Shankar. As all of you know, that the chip design is a very, very unique thing, and totally in the world there are only very few people who are doing it. Most of them, the tape-out has to be done in Taiwan. It's a very niche area, but with a lot that one can do, even that area and other areas using AI, and he has been very actively working in the last 1 decade. So I request him to introduce himself and then his thought process.
First of all, thank you so much, Professor Shastri, for inviting me. And incidentally, it's a decade back when I'm back in my old institute, because after I returned back from the US, IIT Hyderabad was the first place who gave me the job as an assistant professor. That was way back in 2012. So thanks for calling me. So coming back to the topic of today's discussion, so I do not belong to this biochemistry domain at all. I am a pure applied scientist, so to speak. I work in the, as I said, VLSI, AI hardware stuff. But the reason why I think this is also relevant is because all the diagnostic instruments that you use, okay, starting from the basic pulse oximeter to the best possible PET CT scan, these are all done by precise electronic hardware. Recently, my mother was diagnosed, recently, just a few months ago, she was diagnosed that she was essentially missing certain heartbeats, okay? The doctor prescribed what? A typical pacemaker, right? Now, the pacemaker will not come from biochemistry, it comes from electronics, okay? So now the pacemaker, it was really interesting. It has come from a company called Biotronics, many people may be aware of. That's a German company. And since I work in VLSI circuit designs and AI hardware stuff, so I got interested and I wanted to figure out the circuit inside it. And later on, it turns out that the pacemaker that they have got today, they have got a specific unique property which wasn't there a couple of years ago. What it was being said that previously, if you have anyone at home who is having a pacemaker, every time you have to do an MRI scan, okay, that works with high magnetic resonance, right? So that means you will have to switch off the pacemaker. So that means you have to first go to the hospital, switch off the pacemaker, do the MRI scans done, get back to the hospital, switch it on again, and go back home, all right? Now, the current pacemaker that my mother has, I'm telling you this so that you can get the context clear. So the new pacemaker which my mother has got, that has got an auto MRI pacemakers. That is the latest generation from Biotronics. So what they've done is that it will automatically sense any kind of high magnetic zone. So it will automatically sense the magnetic field and it will switch off on its own. The moment my mother is out of the MRI zone, out of the magnetic field, it is going to switch on itself. As a consequence, you can now imagine my mother has been traveling in the flights and that metal detectors doesn't detect even though she has a pacemaker with a battery inside it. Okay, isn't that technology? That's amazing technology. And isn't it coming from, isn't it healthcare? Absolutely yes. But where is it coming from? Electronics. Okay, this is just one example. There are hundreds like that. In fact, MRI scans, CT scans, all the best diagnostic tools are coming from electronics only. So as an introduction, as I said, I did my PhD from ISC, and then I was in the God particle experiment for a while. And then I went to the Swiss Federal for a while, then in MIT for a while. I was in the one of the kind of senior developers in Synopsys TCAD, and then in Zurich, basically in Switzerland. Then I got back to India. My first job was in IIT Hyderabad, as I said. Then I was in IIT Kharagpur for quite some time as a faculty. Then I am right now in BITS. Now, in this whole trajectory of my life career, you will notice I was primarily an applied electronics person. Now, in one occasion in BITS, I had the chance of listening to Professor Shastri's talk on how to use AI for drug discovery. It literally sparked my imagination, and I started to think that, okay, can I use this AI? Sir was speaking about how to use AI to make better chemical reactions, so to speak. I'm not in that field, so please pardon my ignorance in this matter. But in my case, I was thinking, can I use AI for making better circuits? Okay, so that was like 2016-17 time, right? So 10 years down the line, right now, I am essentially publishing papers in AI journals. Of course, in our field, it is IEEE Transactions are the top journals in our field. So the point which I want to make here is that with all my different research domains, research activities, what I would focus on is related to the healthcare. So as I said, as you can clearly understand, how are the healthcare relevant to it? As I said, I'm an applied electronics engineer in this aspect. So one of my projects is something very interesting. I have some friends in care hospitals. Everyone aware, right? Care is one of the very famous hospitals in Hyderabad. So one of the top neurosurgeons over there, he consulted me, and he essentially spoke to me that currently the technology is that he is a top-rated neurosurgeon in Hyderabad, but whenever he has to cut open the human brain for some tumor, whether it is benign or malignant, that's a different thing. Whether it is cancerous or not, it's a second thing. First of all, you can identify that the tumor is there, and then what you will do is you are going to cut open your, it's called jura bone, so basically the skull bone. So you have to open that, and then you'll have to locate precisely the location of that tumor and cut it off. That is basically the surgeon's task, right? Now, care hospitals and many of the hospitals today, Apollo hospitals also, they have got robotic surgeries. Everyone is aware of, right? So if it is robotic surgery, what that neurosurgeon was essentially telling me, my friend, is that robotic surgery will do a very good precise cut with minimum blood loss. That's perfect. But the problem which he was facing is that how to locate that precise zone. Okay, now you understand. Like, the only way you can do that is essentially through the MRI scans. So you go to the doctor, neurosurgeon will basically just look at the MRI scans just like a typical X-ray thing, and then he will try to locate, okay, he will give the certain coordinates of that tumor, and then what he will do is he will essentially control the robotic arms. So what the robotic arms will do is essentially, if you tell these are the 3D coordinates of that, it is going to precisely cut with that, so with a very high precision, which is unmatched with human hands. Okay, no matter how steady your human hands are, the robotic arms will do it much better. The trouble comes is the human eye estimation of that location of that coordinates. Are you getting it? So in my research project, which is funded by this hospital, so what they're telling is that, can you use AI through thousands of MRI scans of infected patients with tumors, of course without the demographic data, where we can precisely locate that tumor. So in that situation, what we found is that we are using something called vision transformers. Sir will be knowing, whoever is in CS. So vision transformer is essentially built for that. But again, if you are doing an estimation with your eyes, no matter how precise you are, you will be going to as close as, let us say, point some millimeters, right? But in the case of vision transformers, you can go into micrometer precision. And then the question is, if you can specifically know that, okay, this specific area of the human brain with that micrometer precision, there is the tumor, but can you cut it with hand? Absolutely no. But that will be taken care by the robotic arms anyways. Make sense? So that is one of the tasks. Just to kind of excite you how electronics can help us in the healthcare. Another problem. Am I taking too much time? Okay, just another problem. For example, is that you might have noticed that many of our senior people, in the morning they wake up and say that I had some problem in my heart when I was sleeping at 2:30 a.m. in the morning. Okay, then what do? You take your aged people to the doctor in the morning at 7 o'clock. The doctor says your ECG is fine. Okay, we lose many senior citizens in the whole world who expire during the middle of the night. Okay, so in our case, again, this is a project which is funded by diagnostics centers all over Hyderabad. So what they are doing is they are asking, is it possible to essentially monitor your ECG, not just BP, your entire ECG. Obviously, you know that ECG is a much better reading compared to just your instantaneous BP, right? So that is the continuous BP monitoring or continuous ECG monitoring is possible if you can monitor your blood pulse rate only, the pulse rate monitoring system. Now, coming back to what sir was telling in the morning, it is practically impossible to find one physics mathematical model or mathematical mapping between the pulse rate and your ECG, right? But AI can help us in that. So in our research, we have we are successful to do that. We have used transformers to essentially map that. So what you need to do is that you have the fitness tracking, right? So fitness tracking do a very good job in essentially monitoring your pulse rate. Check out all, right? So pulse rate, say, what you do is that you put that and you just go to sleep. In the morning, when you say that at 2 a.m. I had some discomfort, all you do is you open up your app, and my AI model will automatically map it to your ECG fluctuations during that phase of your sleeping time. Okay? You just show that to the doctor, and they will be able to diagnose what was going inside your heart when you were sleeping. So that's a real-time diagnostics thing, and we are essentially trying to make a full-fledged chip, literally at 28 nanometer technology nodes. We have done that. So we are in that. So now you can see that's healthcare. Thank you so much. Let's
Thank you very much. So, it's a very complicated things which AI made. Usually we talk about pulse. Somebody has told that it will send 27 unique signals. There are people, some of the traditional practitioners, they look at your pulse and then tell how much of your blood sugar you have and then BP and many other things which are very difficult. But there is a modern medical doctor and who is also an Ayurvedic practitioner and a Sanskrit scholar. They are able to map out, there are 27 signals that we will get, and from there we can decipher the different frequencies. So electronics is something which is very, very sensitive, better in terms of purifying this data. Next, I would like to have, there is one person who was in industry for more than 2 decades, working in drug discovery, also trained as a clinical physicist or a chemist, and got into drug discovery purely from a computational point of view. I request Marty to introduce herself. So how AI is transforming this whole area.
Yeah, good afternoon, everyone. Maybe I'm the only person in this panel who is working in a corporate. And yeah, thanks for inviting me. And okay, so the fact that we are speaking about AI so much, it means there is something really happening. AI is going to be there. We cannot avoid it, whether we like it or not. There is a hype. There is also people who downplay it. So all these are part and parcel of an upcoming area, and it's only the beginning. It's only going to get better. And certain things which we thought were, I couldn't even imagine 6 months ago or 1 year ago, we are doing it now and doing them routinely using AI. Now, AI, when I say hyped or underplayed, I think it's most misunderstood, which is why this hype and underplay keeps happening. It's very misunderstood, and there are people who keep thinking that our jobs are at stake. These are all quite a few things. It's generally the perception in the industry, at least. It's not that. It makes the job much more useful. Doing things which are more meaningful, at the same time speeding up things, at the same time trying to get to a more quality-based solutions. So, I mean, I just realized it is Indian healthcare, but healthcare, drug discovery is part of the entire healthcare. So I'm working with my team members. So I have chemists, biologists, competitive intelligence, structure biologists, modelers, data people in my team. And we do drug discovery. And we do synthesize compounds, test them in the lab, do in vivo, all of that, additional to using computational techniques. So I don't know how much people know about modeling methods here. Modeling methods are basically physics-based techniques. And these are very useful for drug discovery because drugs are eventually very mobile molecules which bind to large molecules, proteins, which are again mobile. And this mobility is tracked by equations of motion. I come from a quantum mechanics background, but this biology was never my forte. but I have got into biology and drug discovery. You can't avoid it. So physics is very important. Surely scientific method, chemistry is important. AI can help make less human errors, make certain decisions which a human brain can't process, and it can also speed up the things. Many of the calculations that we used to do in the past, so there are many AI agents and LLMs, right? And each of it has its own benefits. You cannot use you can't use ChatGPT for everything, right? There are different tools that you have to use. So let's take the help of, I'll take an example of Claude, okay? So, and I'm not talking of coding. I have been a programmer in the past, but now I don't program at all. And even the chemists and biologists in my team now program. We don't need a mathematician at all, for programming at least. But definitely to come up with methods, we do need. And the workflows that we used to think about in the past, what should be the workflow for this target, this disease, we just ask an AI agent. It takes up all the information, I don't know from where, it could be from our own local databases, external databases, gives up a very neat workflow, executes it, and also tells us what to do next. But that doesn't actually mean that scientists are not necessary. It just means that you need a person with the right domain knowledge to ask the right question to the AI, to understand whether the AI is doing it right, AI tool, and also to know what next how to use it next time, what is the next question to be asked. So it is like, so I keep saying, I was the other day telling Dr. Sastry that instead of having humans as a team members, you should start having AI agents as your team members. And give a job to each AI agent, give them human names, call them whatever, and say, please do this, please do this, please do this. So AI can never be your master. It should be used as your servant. Just like the typical way we say that Lakshmi, money, should be used as a servant, not as a master. It should not decide what you want to do. You should use it you should decide and use it to help you execute it. That is how AI has to be used. But AI we have seen that it's amazing. It can do so many things, process so many things given the data, which human beings cannot process. It's too much of, especially when there is a large data. And also able to do tasks which were earlier unthinkable. For example, I can give you a very ambitious thing that we did, just as an example. And we used the crude version. I called ChatGPT free as a very crude AI. Okay, it's just not the one that you should use for most things, but we have used the other tools also. But again, I have certain limitations to talk about everything. However, so we gave ChatGPT a question saying that I don't want to go into details of anything, just that I need a drug molecule for atopic dermatitis. This is atopic dermatitis is your indication. I need the molecule which having good ADME and DMPK properties. This is the question. No other information given. 6 months back, I wouldn't even ask that question. I would think that is a very stupid question to ask any LLM. But the fact that I even thought, or we have even thought of asking it, means AI is really, we are expecting a lot from it, and we are only at the beginning. And it did give molecules, by the way. It grabbed from whichever sources, it gave molecules. We checked our own database, where we have only our own proprietary molecules, to see whether anything is matching. And honestly, there were compounds which were very close match, with maybe an atom or two difference in the compounds. So now I don't know if those compounds will work or not, but the similar compounds have really good profiles. So ADME profile or DMPK, because drug discovery is a very high risk, high return field. And the fact that we could ask such a question and even get an answer, whether it is right or wrong, we did a back check, of course. Is just saying that things are going very fast and a lot of things can be expected in the near future. And just one more minute. I was at a conference in CCMB recently, about 2 months ago, and there were several startups. The conference was for industry and startups in healthcare. And so they invited me for presenting about some of the things that we do. In the startup, there were so many fresh young people who have started the startups and who have been coming up with tools which, let's say, which can help diagnose certain diseases based on, so for example, if you go to remote villages, people there don't have access to doctors and medicine many a time, and are sometimes timely. So they create these apps which work again with the AI. AI is, again, we have to be very careful. Some people mix automation, AI, and databases, everything as AI. AI is very different, right? It's not automations or tools or some algorithms only. So they come up with these tools which can take, for example, if you have an eye disease, it can take snapshots of your eye, and the person can just click it, submit it there, it immediately gives what is the problem, and also connects you to the doctor, who can actually reach out to you through phone and tell you what to do. So these are the things happening in the country here. And AI is being heavily used to actually help people in treating their diseases. Just now we have been hearing all of the people here talking about Surya, for example, how they are actually pinpointing the area to actually, during surgeries, to figure out where exactly, how precise we can do the whole operation. So there is a lot that's going to happen, and it's like 2 months, 3 months is already a huge time, and there's a huge difference. And I think people have to be on top of it, use them as much as they can, but don't believe everything that they do. Use them cautiously, but get the expertise on that. I think besides that, I think we have covered most of the points the panel has covered.
Very happily doing some basic science in Sweden, because in KTH, the place which will give away Nobel Prizes, and he published lots of papers, more than 140 papers, and suddenly settled, wife and daughters are there, and suddenly he decided to come back to India. And when he came back to India, he also started talking about AI, and they recently submitted a large project on some foundation models or something like that. Where, it talks about the indispensability of AI in whatever field that you are working, because his training was in pure principles based pharmacodynamic simulations and hardcore materials chemistry or modeling simulations, multi-scale modeling. And I request Professor talk about the relevance of AI in
Sure, sir. Yeah. So yeah, thank you very much, sir, for this opportunity. Actually, after moving back to India, then I started working on these machine learning, deep learning approaches for drug ability prediction. So I mean, the thing is that I used to go and give presentations, and then people ask, so then how many drugs came from AI? Then when such questions are asked, right? I mean, our answer is not very positive. If you see that, I mean, we are able to narrow down the search space, right? We are talking about a search space which is like 10 power 23, 10 power 12, 10 power 9, right? So you will not be able to screen all these compounds using high throughput experimental screening, right? But then if we can narrow down them to like 1,000, let us say 100, right? Then I mean it is a great success. I mean I rather see this as an opportunity, like use these methods and then narrow down the search space, then you take it to the experimental setup and then validate it. So I mean people question a lot, like is there any single drug which came from AI? I mean our answer is we don't have any positive answer, right? I mean but thing is that there is a lot of scope. I mean now the good thing is that earlier we didn't have so much data, right? So we have to rely on physics-based methods. Now we have so much data, you know, we keep generating lot of experimental data. I mean, so it is a good opportunity that if you have your data, then you can build a reliable machine learning, deep learning model. That's the advantages we have, right? I mean, so the thing is that when we are using it, then you also need to know the limitations, like how it is working, what are the limitations, all these things you should know. You know, we have machine learning, deep learning, we have active learning, we have reinforcement learning, right? We have, I mean, human general intelligence, the very recent technique, like the intelligence which is more like human, right? I mean, we have machine intelligence, but then intelligence which is more like human is that what people are looking forward now. So, I mean, you might have studied about Asimov's. He talked about weak AI and then strong AI, right? Weak AI in the sense like, I mean, it is, it cannot play chess or, you know, AlphaGo. But now we have tools which can play like human, right? They can play AlphaGo like human, and then, you know, I mean, there are like tools which are reinforcement learning based. They can perform like human, like they can do intelligent tasks. So we are very close to it. I mean, the future is very promising. I mean, with that, I will give it to you, sir.
Thank you very much. And we have only one possibility about 30, 40 years before, that we can't do anything in India. You do your education, you go abroad. And the situation is now very different. If anybody gets a very good job in India, they will come back. And we still feel that if someone has a very, very good job abroad, why will they come back? So Shandar Ahmed is somebody who has a very stable thing in Japan. He would have been there even now. But he decided to come back, where he was doing extremely well at that particular point of time, to look at the huge amount of data that comes in biology, at organism levels, at cellular level, at transcriptomics and multiomics levels. While we have the DNA, and some parts of that you understand, and then you say that that's a coding region, and some part of that you don't understand, that's a non-coding region. Even central dogma of biology, where DNA is important or RNA is important, now in the last few years, the RNA biology has become so important. And it was at that particular point of time, Professor Shandar Ahmed has decided to come back, and now leading a very, very big lab in the last 1.5 decades.
10 years.
10 years. So he's a person who has come back to India and then made an impact. There are a few people like him who had very good jobs in Japan, and after you, Michael, Rohita from Madras, you know, Pavan also, because these people were there in Japan for several, established themselves as scientists. So he has his own perspective of data, biological data, and now the AI in data. The request Shanda.
So I think you have been listening to science since morning. I'll take a risk of reading some poetry because I have been introduced as poet for so many times since morning.
Yeah. First time when I saw him about 10 years back when he came to India, he gave me a book which was on English ghazals. Ghazals I know, but English ghazals I don't.
Yeah, so the poem reads like the one that I want to share with you is, it's little Urdu, I'll translate it for the benefit of most of you. Talatum haad se ilzam gariyan. Talatum means conflict, accidents, accusations and complaints. Talatum haad se ilzam gariyan, सब उसके साथ रुखसत हो चुके थे, यकीन था अब न हंसना है न रोना, कुछ इतना हंस चुके थे रो चुके थे. So I am saying this in the context of my lecture in the morning. I already spoke so much that I was not thinking to speak again. So this couplet actually talks about having spent so much of beautiful time with a person in happiness, in sorrow, and in anger, in love, that it felt like there will be no such emotion anymore. But emotions don't go away with a person. Emotions don't, and passion does not go with the lecture. So I spoke about AI in the earlier lecture, and the question in the current discussion is AI in healthcare. So I see it in a few from few perspectives. First of all, what AI can do, and secondly, how AI challenges us in the field of AI, how we do as a scientist, and also finally the what did I say? I had one more thought. So is AI different from any other technology? So I'll take these three questions. First of all, what AI can do. For most of us, AI is you can use AI without knowing AI. And we many times say that we know AI, we use AI, but we don't really have to know AI for using that. We are editing our photographs on a phone, and we are using AI tools. So can we say that we are AI experts? Or we are same way, when you are doing something on using an AI tool, do we become AI expert, or what kind of expertise do we need to do that kind of work where we are not really developing AI, we are AI users? Is AI user any different from any other technology user? That perspective has to be understood. How an AI user different from any other technology user? Any other technology user looks at the data, if it is a data science problem, or if it is any electronics problem or robotics problem, in a more well-defined problems like we discussed, physics, mathematics, and so in the absence of an AI, we see the problems in that perspective. This is the question, and we need to have this knowledge, and this is how we can answer. The AI way of thinking is slightly different, and that is that we have this data, this is what we want to answer, we do not know what is in between, create a black box that can connect it. So creating these black boxes, this is what AI developer will do. This is not what an AI user will do. AI user will get the black box. So now, first of all, the AI user has to understand that there are black boxes available and they can solve these problems. So what are the black boxes available to you? That is all you have to know. So you become AI expert without knowing AI. You only have to know the list of tools of AI, and then you have to use them. This is one thing. Second, the questions that AI is addressing, are they different? Are they any different from the questions that are addressed by different? So you have molecular dynamic simulations, you have molecular docking, you have any problem in science. Is AI addressing any different problems? Perhaps AI is addressing very similar problems, but with a greater efficiency, with a greater power. The questions remain the same. How AI user, AI developer, and somebody, a professional in AI, has to think about science today does not have to think in these ways. These are the ways anybody who was trained in any subject can think. Somebody who has an expertise, who has a passion for it, has to think really in another term which is called disruptive way. You have to think something large scale, because the science method is changing from the mathematics method, from the physics method, and the rate at which it is changing, transforming your subject, is enormous. So you don't have to think incrementally. You have to think in a disruptively. So you, for instance, you are thinking of designing a medicine for curing a cancer can be diagnosed early on, 1 month earlier on. So can you diagnose a disease, or early diagnosis, as you say? So what is the meaning of early diagnosis in the absence of AI? The meaning of early diagnosis in the absence of AI is maybe 1 year before, 2 years before. Early diagnosis in the case of AI is right at the time of birth. Can we predict when a child is born, what will happen when he becomes 30 years old or 40 years old or 50 years old? So these are the disruptive questions. Think of technology in a disruptive way. Think of the questions in a more challenging way. Can we try to increase the longevity? I mean, Indian population, an average life expectancy was in 30s when we got independence. We are in 70s now. So incrementally, without the AI, our life in longevity, life expectancy has increased from 33 to 40. Now, with the help of AI, do we continue to go on that same curve? No, we should be thinking about, can life expectancy be increased to 200 years, 500 years, 400 years? These are the questions that people are actually thinking. So first think how AI should impact your thinking is think in a disruptive way, think in a very fundamental way how things will be transformed, not in an incremental way. This is the third part of what I would like to say about it. So this is, thank you.
Thank you very much. So now I will take 2-3 minutes to summarize. So AI is an angel or a devil, we don't know, but it is going to stay with us. It all depends on us whether we make it as an angel for ourselves or a devil for ourselves. Because any powerful technology can be used in ways that is useful to us, or can be used in a way that is harmful to us. So there are civilization which has grown up, and what is happening to the welfare of the people. And I think the welfare is very much dependent on how positively you use your technology, right? So now the AI is a powerful tool. So there are some things like in food security, several technologies play a very important role. And maybe AI can be used in a very effective way. Because we all know that about 100 years before, our, as Shandar said, our life expectancy is 30 years, and we are just about 2 billion people. But now we are 4 times more. But we have a lot of food security, and we have many more amount of clothes per person, many more amount of square foot of constructed area per person that is there. So what is happening to the things which are making us more comfortable? They are all increasing. So we will have to see the energy or the 17 sustainable developmental goals, because about 50 years before people were not talking about sustainability. They talk about roti, kapda or makhan. Now they are talking about sustainability. So we have to talk about the healthcare, we have to talk about our water, we have to talk about our energy, we have to talk about our justice, ethics, values, and we need to talk about many other issues. And these are sort of getting more and more challenging because of the complex ways in which the human society is evolving and civilization is evolving. And they are becoming more complex because of the technology that is there. But the complexity with which we create a problem is not enough to solve that problem. So we just have to be very, very good in utilizing these technologies for human welfare. It is absolutely not possible that no, I will not be able to. For example, without electricity, people have lived much better 200 years before. That's what somebody will say. But is it possible for us to say that I don't use electricity? Without landline phones, 99% of the population is there in India. But then how many of us can survive without mobile phones? We never ever worried about the drinking water issue. When there is a water, we used to drink from there, right? Now we are very much used to drink the RO, which is very bad, and the distilled water is very bad. Putting a plastic bottle is much more horrible. So we are making our life hell. And the civilization has grown to such an extent that in the summer, people would like to put their air conditioners 90 degrees and 80 degrees. And in the winter, we don't heat it in Canada and Russia. They would like to put their air conditioner at 25 degrees and 26 degrees. So this is what is happening. And sometimes producing electricity is important, but saving it is more important. A
simple technological revolution like LED lamps, replacing the other thing, has made a huge impact on the electricity issues, which we all know in the villages and things like that. So there are a large number of problems that are there which we need to address with intelligence. Whether it is artificial or natural or unnatural or supernatural, whatever it is. Is intelligence, how do you define it? I think that intelligence at the best can be defined as trying to have correct decisions for your welfare and the system's welfare. And that may be probably equal to common sense. But usually when the intelligence of the scientist increases, they will lose the common sense or the people. I don't know what's very important, and I am always afraid of this fellow recording, and then I will say something about Iran-Iraq war, because my love for Donald Trump is so high that he will try to actually put all of us into a completely different ballgame. This is the most advanced country in the world. So what exactly is happening? So we all know that we have heard that 5 years back or 4 years back, ChatGPT was consulted to resolve the Russia-Ukraine war. Yeah. This was probably the most intelligent solution that anybody can provide. And it is also well documented that in the recent attack of Israel and US on Iran, Anthropic cloud was very strongly used. In the same week that Trump has banned Anthropic cloud, and his own government had to use Anthropic cloud to have a warfare. When we are having an AI in healthcare the first day, I requested Srijit, please, can you please give my slot and I will exchange the other slot. There was a big conference which was going on the space technologies here. The DRDO, ISRO, and many others have come up where they are using automation, navigation, and AI is playing a very important role. Topmost guys have come to IIT Hyderabad. Yes, exactly. This Anthropic cloud has made our life so. Surya was saying that, yeah, I am the person who is only doing the code, none of my students can do the code. I was trying to pull him relax. I said, yeah, Surya, you are a very different generation. The Gen Z people, they use code. Why do they write the code? Or something like that. So now the way in which things are happening are very different. I repeat what I said, that education is nothing but awareness. We should be very well aware of what is going on, and we should try to have a clarity that how do we use this technology which is around. Go to the roots and try to understand that all the methods that worked before need not work now. This is a complete paradigm shift. Life is very different. Thinking is very different. The way things are happening are very different. Before ChatGPT and after ChatGPT. But after ChatGPT, as many people were saying, that every 6 months things are happening in a completely different way. What you are now will be, all these modern technologies will be outdated in the next 3 months to 6 months. The pace at which things are changing are different. But what remains is your intelligence, your common sense, and your ability to look at a purpose-oriented thing. After all this talk, Professor Shankar Ahmed has put the last slide. Forget about the technique, focus on the purpose. Remember. So we need to know that all these technologies are there for our human welfare and our happiness and our enjoyment. And I hope that universities and teachers like you will carry the positive mantle and then create better students who will be able to use the technologies. We already missed the bus industry 1.0, 2.0, 3.0, and 4.0. Let our country use the technologies for the benefit of every single person there. These technologies should be the greatest equalizers where the differences between the poor and haves and have-nots should decrease. Then and only then a country will progress. If we have a large number of people going to bed without proper food and they don't have a proper bed, they don't have a proper house, no country will develop. And we need to focus on these types of things. And thank you very much for the great opportunity. And all of you who has left, and only very few people are here, so please carry this message. And then I would like you, all this AI in health, to have a WhatsApp group. And if you want, you can add Srijit and me and others also. And we will be very happy to help you or work with you. It is our responsibility as a hub and spoke model that to mentor you, and we are very much looking forward to have a stronger relationship with this spoke institute so that together we can make a difference in our ecosystem that is in AI. Thank you very much. So with this, we would like to have a few questions from the audience. Some of you should have asked some questions. We spoke not because we have something, because you have to speak, that's why we spoke. Now you have to ask questions. Even if you don't have some questions, you please ask. For the sake of
We had not even collected some questions.
So you said before that we should, when we talk about early detection, you said before that can be detected some disease after 30 years or point at point. So I'm asking that is that a morally or ethical way to diagnose?
A lot of work is going on in the digital.
I'm asking what is your opinion? It's morally or ethically correct to before birth, after 30 years?
No, I didn't say before birth. So your moral question will only arise if this is being misused. For example, in making decisions about to having a child or not. So this is, of course, there's no dispute about it. This is not morally right. So, so all those ethical concerns and all, they will remain valid to any questions that we raise in the healthcare. So, including AI.
Hi everyone. It's more of a logistic question. I'm currently a PhD candidate at University of Buffalo, and I'm working here on a research project at ANRF lab under Dr. Wanedu. So my question is, like in US or other countries as well, the healthcare data is very easily available. But let's suppose the EHR, electronic health records, or the normal patient data, which obviously we de-identify and then we use it. But I think at this point, or maybe I might be incorrect, I'm trying to gather as much information as I can. What is the entire situation in India? Like, is the healthcare data this readily available, like it is in other countries? Let's suppose USA, because if data is not available, even if we come up with like different we are being ambitious and we want to do this and that, but if data is not available readily, then what's the point? So that's my question, that are we going towards that point where yes, data is going to be that readily available? So anyone can answer.
It's an interesting question. We can have the data, but do we understand the data? Most of the advanced countries, they don't have any clue of what is happening. One of the most collapsing healthcare system is United States. In United States, every geriatric patients who are above 65 years, they are spending about $1,800 to $2,000 per month, which is leading to the collapse of the insurance and government and all these policies. And I know that there are some private organizations which are taking a cohort of the entire group. I know that there is one group which have taken about 10,000 people, geriatric patients in Las Vegas, where those group has 500 doctors. So they are taking about $1,500 from the agencies that they will take care end-to-end thing. But the main thing is hospitalization, to have to go or to not to go. And then what are the periodic checkups that are there. Many data is there, but we are not able to interpret the data. So now the question is, for the healthcare, data is not there in India, definitely. But what type of data that we are talking about? We are talking about the general medical data and the whole genome sequence data, or there are a lot of other data, because some of the people who are having the oncology patients, you also would like to have a single cell transcriptomic data, or you can have a huge amount of data, and all these data are very expensive. And people are having it, and in India a lot of business is going on that this data people are also selling. And India is 1400 million people, and to get the data, for example, there is an India Genome Project, which government invested 500 crores. You are also a part of that. 500 crores, they are able to get 10,000 patients. Not patients, actually 10,000 healthy individuals. So if you want to really have any substantial data, it will be a large, tall order. So I don't know, the question that you are asking, the data is not available. But even if the data is available, we probably should come up with different types of a conceptual thing. Maybe Shanda.
I think India has a lot of data, but how well is it being
Yeah, I'll explain. I think I'll introduce some of the initiatives of the Government of India that have gone in this direction. So there is definitely a problem of data, biological data as well as the health data. So health data problem is there are no registry systems in the hospital, so we cannot have, I mean, even with everybody's intent, we cannot have the data unless we have a registry system. So those are weak. They are on the individual collaboration level, it is there. But even the data which has been publicly funded as part of research projects, that researchers have not deposited with any agency and not shared. So that problem has been realized, and I am part of the data management group of Department of Biotechnology. And there is now a center called Indian Biological Data Center, IBDC, which is supposed to be the center where all the data which is generated by the public funding should be deposited, and more and more funding agencies are insisting that researchers should do it. Their funds will be curtailed, or they will not be given future projects if they don't do it. And already substantial amount of data is there. Genome India is one such data which is there. The imaging data, the X-ray, mammography, and the whole slide images, all these data are being compiled, and a lot of that is available. And there are two levels of access. One is for the public, which anybody can use, and other are for the academic institutes for research purpose. So I'm just this is just a kind of snapshot of the initiatives which are being taken by the funding agencies and by the regulatory agencies in trying to get the data and make it accessible for researchers.
So I can only share with you the solution that we have worked out in our research. So all our research is being done in India in bits. So basically what we try to do is that if you will look at any of the AI techniques, especially the generative AI, there will be several hidden layers. All of us know that, right? So primarily what we do is that we will train let us say, except the last and the penultimate stages, we will train based on whatever publicly available data there is. Let us say US has the data. For example, in our case, we are also using some databases which were published in Japan, for instance. So we are getting whichever is available. So it's a kind of a note for anyone who wants to pursue this kind of research in India. So the solution is that, of course, the best one will be, as Professor has already shared, if we have a better database from India itself. If not, then the way out is you train your model like until the last but one stages based on the data which is publicly available. And then once you are getting it within, let us say, 10 to 20% of accuracy range of the predictions. Then you fine tune the last two based on, let us say, 1,000 or 5,000 data set which is available from your MOU which you are having with some private hospitals. So in our case, what we are doing is we have got multiple hospitals over there. But again, those hospitals, even if they share, because that is some kind of collaborative project, right? But those hospitals will be providing a few thousand data sets, right? But again, remember, one of the major issues you have to have that MOU for is that you should not share any kind of private details about the patient. That's the major criteria. So, so that data set will be very less. But that less amount of data set is good enough to fine tune your model. But the actual data set which is available on the internet, public databases, that is sufficient for training roughly the majority of your hidden layers. So that's how it works pretty well. And finally, at the validation stage, what I'm talking about is a testing, training and testing. Then at the validation stage, nothing works best rather than take your laptop, go to the hospital, check the measurements and do it right there. That's the best proof of the pudding if you are trying to do some healthcare. Okay, thank you.
Thank you, everyone.
Good afternoon, everyone. So I have two questions. Yeah, I'm Dr. Shiv Shankar from Thematic Harvard. I have two questions. As ma'am rightly said, we use AI tools but use them cautiously. But yeah, so I just want to know actually where to draw the line actually. Because whenever we discuss with the students, because I'm from education academics, so whenever we discuss students, so students always use Gemini or Cloud or ChatGPT, and then also during lunch, Dr. Surya was saying, the students they kept on saying that okay, Google Gemini. That's true actually. So where to draw the line, how to convince students how to use
Yeah. No, continue. Yeah.
the second question is related to this healthcare black magic of AI. So do we need to understand the physiology, or do we ignore the understanding of physiology if AI works? Because AI sometimes AI does black magic, so we don't know the answer why it's happening. So do we need understanding of physiology, or in this way, ignore the understanding of physiology if AI works?
Okay, the first question. There are two things called as training and validation. So AI actually gets trained on the data or the information that you give. It tries to understand how you think. And there are a lot of algorithms that go behind it. So you need to validate, keep asking, train it to think the way you want it to think, you want the answer from. And I don't think you can blindly believe it. There has to be some sort of a quality check done. That means you don't have to go through the whole thing and test. You can pick some pieces of data here and there and check, okay, is it doing right? Some extreme points, some limit points, and then decide whether, yes, you can believe this or not. So there is no hard and fast rule where we can draw a line for these things. It is case by case basis, and also it depends on how you train, and you need to keep validating it. So that's the stage it is in now. So whenever we again do a validation. And when you keep validating and then you keep questioning it again and telling it, look, this has gone wrong, or this doesn't seem to work, then you're training AI, the agent, to think and understand the way you're. So it starts getting more and more accurate. But when I say accurate in the terms of what you are thinking it should be doing. So yeah, so accurate in the sense what you're thinking, and accurate in the sense how you train it, basically.
As a an expert, for example, if I am an expert in some field, and if your AI says something, okay, I know whether it's telling correct thing or not. But if
Yes, so experts are needed. So we can never do away with domain experts. So that's one of the things why AI cannot replace everything. You do need experts. Yeah. And yeah, I think you're talking of hallucination. What?
The black magic of AI. So do we need a physiological understanding if AI works?
I think we always need to understand, have a domain knowledge. There is no way that you can replace AI totally 100% with anything. But again, if anybody wants to take this.
I can try to explain one part. Suppose AI, how will take common person is a technology, and the question is coming that how will you, when I will use and when I need to use or will use or not. Suppose here we are sitting there, you see that in the chairs are there, two chairs are there. Here the chairs are there, the chairs with a wheels are there. Now question is coming that which chair will you use? Now there is a cognitive is there actually, a cognitive system if you tell it. So human intelligence are there, and there is a human brain is there, human memory is there, many things are there. So there is a connectivity is there when you talked about the cognitive science. The question is that technology is there, technology will use or not use, that is a connection is required. Okay, and then there is a barrier. This is if you ask that any philosophical question or philosophical answer, and technology is a very realistic. You understand? This is realistic. Because someone is making a technology and there is ready-made. Someone will use it, so they are not making it. So who will use it? So they have a different perception. How will you take a decision whether it is required or not required? So suppose you are telling that I am doing a research. Now I think something and take a decision. It is my outcomes or it may. Now I use that Gemini and then check that what is giving that. Now question is coming that whether you will boldly use that your AI outcomes or you will use your own. So that is that. Another is that your brain decision you will take it. That is a different prospect. And this prospect, Shastri sir is also telling that any technology is coming and use evil and that heaven both are there actually. Good and bad is there. How will you utilize that depends on that human that how they will take it. That is my question on a philosophical answer. Another is that very realistic things. Even starting of that nuclear the research, that atom bomb to that your nuclear power. So which way you will take it, that is depends on you. So AI will be there. It's like a shadow of the person. You cannot remove, but they utilize the human beings.
Yeah, so you already got good answers, and I'll put it this way, that AI is not a substitute for domain knowledge. You should not think that AI is here, you don't need to do any experiment, you don't have to understand physiology because AI can give you an answer. Ultimately, we would like to act based on the explicit knowledge and do things based on that. So there are two things where AI is replacing that effort. One is that AI is ahead of knowledge. That means you do not know the physiology, but there is data somewhere, and there are data has been already encoded into some models which will give you an answer, which is also coming from this knowledge and this data. And then before you can actually understand the domain relationships, the physiology or anything that is happening, you can get an answer. When you used to do clinical trial, for example, clinical trial is a knowledge, is a phenomenological observation. You observe, you give this medicine, this is what happens to the patient. You immediately stop this drug will not be approved. You don't go for knowing the physiology, why this drug is not working. You cannot wait for that. You take a decision based on what you observe. Same way AI can give you answers before you actually understand the physiology. Second is, your knowledge is encoded in the AI. Your LLMs, etc., they have already read through the literature, huge amount of literature that individuals will read. These models have already read them, and they will provide you a summary and an outcome based on what is already there. So the AI answers that you are getting are not from vacuum. They are based on the knowledge which is there. So remember 3 points I made. First of all, AI is not a substitute for knowledge. Second, AI is ahead of knowledge. That means when you do not know things explicitly, you can use AI and make speculative predictions, speculative or sometimes very reliable predictions. And thirdly, AI has models, particularly language-based models, have already encoded a lot of knowledge from huge amounts of literature, which you cannot practically scan through in realistic amounts of time.
But earlier in the morning, Sanjay was telling from that 1.4 nanometer.
Yeah, just to add to what Chandra sir was telling, let me first be very clear about this. What is the full form of GPT? Chat GPT mein GPT, anybody? Generative pre-trained transformer, pre-trained, please highlight on that, okay? So that means, as sir was telling, it is essentially a kind of knowledge base, so to speak, which is based on the training which it has done on the basis of the literature which was available until the snapshot a few years ago. So if you are making a query in ChatGPT right now, it is going to give you the results on the basis of the training which it has done, which has pre-trained until let us say 1 year ago, 2025 or 2024, all right? So now if you ask, okay, you published something 1 month ago, it's already in the literature, but ChatGPT hasn't trained it as yet. The chances are ChatGPT will give you incorrect answers. The correct answers are available in your ACS publications. Notice this, because ChatGPT hasn't learned it yet. But in the next version, 1 year later, it is going to train itself. Is that part clear? Yes, that is what. So if you notice about that, for example, whatever textbooks we learn, okay, let's be real over here. Those were written in 2000 or let us say 10 years ago. Right? So that means if you are talking about the latest research, then you have to go through the journals, right? But if you want to learn something about Newton's laws, well, ChatGPT is very good. Okay, so now the question which you have to ask is, today is the time where we really need to come out of our bookish knowledge and focus more on our intuition, our innovations. Now, if you talk about whether our domain knowledge is relevant today or not, now the point is that domain knowledge is more relevant today because we have to depend on our ingenuity. Because suppose you ask a very young kid of 5-year-old to memorize the periodic table, all right? ChatGPT will do obviously a million times better job at that, okay? But can I use those elements in the periodic table to make a new compound? Okay. Probably that requires human intelligence, that requires ingenuity, that requires your expertise, right? So you cannot go beyond that. Even in the case of coding, we say that people are losing jobs because of coding. The point is, what is a code? Code is not a Python script. Code is the algorithm behind that Python script, okay? So when I was working in Synopsys for a while in Zurich, as a senior developer, I had to actually write the flow chart actually. So my job was, I was essentially using this whiteboard and developing the numerical methods. At that time, there were no AI. So I was using the whiteboard to write like huge flow charts, okay? And I would ask my BTech engineer, BTechs, computer science, who will do much better coding than myself. But I was there as their boss, who will be basically using pen and paper or a whiteboard just to put that algorithm in place. So now that algorithm to Python or algorithm to C++, algorithm to Java can be easily done by ChatGPT. They will do it a much better way than a BTech engineer. Okay, but the original way how to solve it using an algorithm, that requires your computer science expertise. So we have Sujit sir over here. He's a CS professor. He's an expert in that. So you will notice how to make the most efficient algorithm using the complexity, time complexity and all. So big O notation, that is where human beings come into the picture, not AI. AI will do the coding, okay. As sir was rightly telling, after a few days, I will not code. My students will use ChatGPT to do the coding, but I will be doing the flowchart. You understand that algorithm and flowchart is what is the basis. All AI is about that flowchart, that algorithm. Transformer is an algorithm, not a Python code. Okay, please understand that.
we should not forget to pay the tribute to the technologies which are coming in parallel other than AI, which have made the AI possible. So the technologies in the field of biology, single cell sequencing. If AI, whatever AI could do, if single cell sequencing were not invented, then we would not have this data and you would not have these models. If special transcriptomics did not come, we would not have this. So the rate at which the actual technologies are also developing side by side with AI, they have to work together hand in hand to make discoveries and to advance our knowledge.
Regarding like data you mentioned, India have already IPTC, right? Sir, but I feel like still we are suffering a lot for data. Like, sir, there is also large procedure to get data from here, and India have a lot of initiatives like Genome India and IPD for protein database. But still, sir, there is a large process. Like, we submit a proposal and then get data after 1 year, and as a PhD student, we can. Sir,
Yeah.
And we know that disease biology manifests through genomics, like genetics and environmental factor as well. But as an Indian student, we mostly use other country data. So I think like if we start something like NCBI Geo platform or something for Indian, so it will be better for us because without data, this JNI or something, nothing will work.
Yeah, so this is this extension of the same question. First of all, the problem is cultural. We don't have the cultural. Why do we want to hide our data, or why we generate a data in our lab? We don't want to share this data with any other researcher, or we write a software code we don't share with anybody. There may be a number of reasons, but two prominent reasons. One is that we are insecure, that we are not confident of our data, that somebody else will find a flaw with our data, so we don't want to hide, we don't want to let anybody have it. I'll explain, come to your full question, then you can ask your subsequently. Secondly, we think that we have generated the data, so it is our property, even though it has been funded from public resources. So for a long time, you would see, if I am sitting in DBT committees also and in this IBDC committee also, huge amounts of money has gone into just developing the databases. There are projects which have been titled development of a database of such and such things. But this database never came into public domain. This data retired with the professional who actually got this project. So this is some kind of an unethical practice on the part of the researchers who have taken huge amounts of public money and have never delivered on the databases that they promised to develop. So this is, I'm saying this not to bash them, I'm saying this to encourage you people not to be one of them. So this is the goal of this. But now the efforts, IBDC, the time that it takes, we had a meeting of IBDC only 2 days ago, and there we discussed this. IBDC now the management mandates that any request that goes to IBDC for data sharing should be cleared within 45 days. And we decided to reduce it to 30 days. So any authorized request, there are two types of data. One is the open access data, free access data, and another is the restricted access data. So even for the restricted access data, if you are a researcher working in an Indian university and you technically qualified to have access to this data, your request should be approved within 30 days. It is currently 45 days. It should reach 30 days in a matter of time. So 1 year will not happen now.
Final question.
Sir, I'm Dr. Arnav Stanley from Jain Johannesburg. Actually, I'm using this AI tool from a long time. My perspective is, I want to get the data, but whatever is my research, I'm going to describe it as an entity. I don't give any subviews or anything else. Just I'll describe it as an entity, especially towards the VLSI side and towards semiconductors. And then I ask them that what is the flow that I can get it at the output. So that it is going to give the code. After that, then I'm going to personally involve that whatever in my logic is there into that one, then I'm going to simulate that. So to some extent what you're talking about is after 1 month it will get trained because the secrecy is lost once we are going to open up our thought. Is it so, sir? And this is the right process that I'm defining it as entity inputs and outputs and following the way.
No, so basically, if you talk about any of the VLSI industries, the standard way, if you think that you really have a novelty in this, the first thing you should do is that you first file a patent for that, even before your publications are done. And that is the standard norm in any of the industries. Madam can also support this. So first thing is that if you think that it is really novel and it can be worthwhile putting it into the, industries might be interested. So you should actually speak to the legal attorneys about this and get a patent done. So once the patent is over, immediately you submit it as a journal, and then in the paper, what we usually do is that towards the footnote or towards the conclusion or some place over there, you can always write the data is available on request from the authors, or otherwise you can also put the GitHub page where you are essentially producing all this. GitHub, everybody knows about GitHub, right? GitHub. So GitHub is a very, very standard platform for doing it. In fact, in many of the Nature publications, in one of our work, we are trying to put it in Nature Electronics. So over there, they are actually requiring us to show the, as I said, the proof of the pudding in going into the real hospital and doing this thing, right? So we are recording it, video recording it in real time. So that has got no relation with how your model is trained and all. All those details are there in the paper. Okay, but whether your model or your circuit or your drug discovery actually works in real life is essentially putting it on a video record and doing it. And that is essentially published in GitHub. That reference is produced in the paper. And in fact, that can be done in your patent as well. So that is only the very validation, as ma'am was telling. It's a validation that your proposal or your patent actually works. That is a very, very standard way of doing it.
Yeah, that's not my problem, sir. Actually, I'm afraid of keeping that perfect technology through which I can make use of the AI tools even better. Because partially I'm using it. I'm using it depending as an entity, and remaining one I'm going to make it with the AI. But the exact thing I have been pending. Again, I have to map it with my inputs, with my outputs, which is real work, which can be done within seconds by the AI.
Okay.
But I'm afraid of doing that one because there has been something that has been there. And also it has been leading to another research.
But if that is the case, then you can of course put it on GitHub, as I said. But the only thing is that if, with all due respect, if that is the case, if it is so easily reproducible, is it really novel?
Not reproducible. I want to tell that it can be copied by by any of your AI tools.
Yeah.
And it can be given as a answer to any of the questions which may be asked on the table.
Okay, in that case, what I'll suggest is you should always, it's better to license any of the LLMs actually. We are having a discussion. If you license it, any of the, whether it is ChatGPT, Gemini or anything, you purchase Google Suite, for example. Everybody knows. The whole reason was that he wanted to entirely monetize ChatGPT. So some of the lead developers of Open ChatGPT, they formed Anthropic. And if you use Anthropic AI, which is our Claude, in Claude AI, you will find an option. You go to the settings, the free tool itself I'm talking about. If you license, no problem. Okay.
License in the sense?
You purchase it. You will find some money you have to give monthly, yearly,
That's a subscription.
There is subscription, yes.
Even I'm doing that.
Yeah, then it will not be trained at all. Yes.
We are very in all of these corporates. We are very, very careful with the IP. We have a lot of IP of the code, IP of the research outcomes, and all of these AI agents have a very secure version through which your data will not get leaked out of the domain that you define. So we all do it. It is routinely done in all corporates. Yeah.
That's it. I had to map it once again.
They'll help you.
No. It will do. So it will not leave the servers. It's something similar to if you are having Gmail, your emails are not accessible by anybody else. Okay, similar thing will happen for the LMs also. But if those of us who are using the free version, not the subscription, you use Anthropic, that Claude AI, go to the settings and you will literally find one check mark is there, whether you want to use these chats for training later on or not. If you disable that, what is the problem you can say? None of the chats will be read by Claude AI anymore. So that means today you are doing a request in chat Claude. Tomorrow if you want to make a new chat, for instance, it will lose the context which you have done today.
It's called a session.
Exactly. It is basically session based.
I think some of the fear is really exaggerated, because if these models were using every uploaded data for training, it would be very easy to distort those models. You keep on putting wrong data, and these models will go havoc. It is not like this. Every data that you upload to a model is not usable. There are many standards which are required before any data will be usable for training purposes. So some of the fear that we will make a query and this data will become a part of their training models is somewhat exaggerated, because every data we upload is not usable for training.
Yes. Not a trainable data, but it can be a database.
Yeah, it can be. But as I said,
but how do they know that whatever you are uploading is a correct data? So they cannot just use it for training. You may upload some wrong data. So that means you will introduce errors into their system. No.
Automatically, we are also getting the wrong data. We are the one who are going to justify the things at that point. Sometimes we may get the wrong data also. We are going to justify by intention also sometimes, doing with the small model.
I'm not ChatGPT, but if I am ChatGPT, I would be very reluctant to use a publicly uploaded data, because I do not know what is the data upload, what is the quality of that data, what is the authenticity of that data. Without having that, I cannot use it for training.
simple ma'am, you simply use the subscriptions. If you use subscriptions, that is the inherent clause they mention. It will not be used for training.
One more thing, actually, you are talking about just it's a database, training of the data, black box, everything. So where lies the question of the algorithms which can be used to simplify the parameters has been simplified. The data is scarce, because you are telling that medical data is scarce. I am not towards the medical field. Medical data is scarce. Then still there is a potential that we are going to extract the best parameters, best algorithms, which will be mapped better on a simple AI than that of a complicated AI like that of your multimodal things, which will give the better things than that of things. Why we are leaving the algorithms?
So this will be the
data is scarce.
This will be the question for T. Okay. So all good things should come to an end. So the GPS, yeah, we will discuss over T. Okay. There are a large number of people who had collateral damage to their vehicles and to themselves because they followed GPS. They went straight into the lake, many other things, and you cannot put a case against GPS for that. And there is also a responsible AI. There was a big discussion where Arul Murugan and I was there. There was a French guy who developed this. It is unethical to get an answer from a ChatGPT. How do I kill a person? Right? It will not give an answer. But you can try to create a story in which you wanted to create two characters and one character has to kill another character. It will give all the strategies of how to kill the other person. So there are ways of circumventing things. No, this will be OT. Okay.
One point. We actually joke in our office that the future will be the future for hackers. How can you hack all of this? So the hackers will start using AI for all of these. So the future will be for hackers. What if your money in the bank, if all the information is given and the AI agents can hack the money? So it's a joke. It will not happen.
The first question is different. Second question is when the data is scarce, Why don't still be the text?
That's why I don't want to allow this question. So we will have it over tea. So not only future, the past is also for hackers. Ever since this funny field called computer science entered this, only hackers were there. And the first hacking thing is every smart student used to hack the supervisor's email and the password. And then they will know everything. So past and future is always for the hackers. So now we will stop, and then there's a fantastic. Thank you very much for every single panelist for their very short notice, and smart people. All this has come because of the game theory, and that people wanted to do that. This we know how things have happened. This is all for fun, and we will continue to have the fun over the tea. And before this fun, Professor Srijit wanted to do something, and I will give it.
Oh, okay. So, thank you all for attending this session, and thanks a lot for panelists for coming here in the short notice. So we have some mementos for the panelists. If you can give to them, that will be great. Like first, I would like to call, Shaz. No. Please. Sure, please, Chandra Ahmad, please come. Yeah. Next, I would request Arul Murugan. Requesting Motahar Rasa. Sure. Surya, please. Something special for madam. Yeah. Yeah. Thank you all. So we'll be closing this session. I would like to request to get an opinion from you. Like, we will be providing you the certificate of participation. Would you like to get it now or after the tea break? Maybe we'll have it now and then we can go for tea break. Is it fine? Sure. Yeah. These certificates, right? Sure. And maybe you can also give these certificates. So I can call one by one.
So we can call like this also.
That also, yeah, that's fine.
Akri Naresh.
Dr. C. Dhananjay Kumar. Dr. Y. Dayanand Kumar. Dr. S. Aruna Mastani. Dr. Malay Kumar.
Sorry, we will discuss over this.
Dr. Duba Charla. Dr. Siva Shankar Padya. Dr. Akriti Srivastav. all the participants can take the certificates from outside. Thank you.
Chinmayanand is not here. Huh? We will have a picture of all the participants who are a gift. We'll take it out from this.
So embarrassment is less. If there are 200 people, I will be embarrassed in front of 4 people.